You are listening to Mastering Redis, Performance, Patterns, and Best Practices. Like and subscribe to keep up to date on our latest audiobooks. Mastering Redis, Performance, Patterns, and Best Practices. Chapter 1, Introduction to Redis, Why It Matters. Every successful software application, from a simple mobile game to a sprawling enterprise system, relies on efficient data management. In today's fast-paced digital world, where users expect instant responses and real-time interactions, traditional databases designed for durable storage often fall short of performance demands. This is where Redis steps in, offering a lightning-fast, versatile solution that has become an indispensable component in modern application architectures. At its core, Redis has a rather unassuming identity. It's an in-memory data structure store. But don't let that simple label fool you. What lies beneath is a powerful, flexible, and surprisingly enduring technology that consistently ranks among the most loved, used, and wanted databases by developers worldwide. This book will embark on a journey to unlock the full potential of Redis. We'll move beyond basic usage to explore how you can leverage its unique capabilities for peak performance, implement sophisticated design patterns that solve complex architectural challenges, and apply robust best practices to ensure your Redis deployments are secure, scalable, and highly available in any production environment. 1.1 What is Redis? A high-level overview. Imagine a super-fast whiteboard that your application can write to and read from almost instantaneously. That's a good analogy for Redis. It's primarily a key-value store, meaning data is stored and retrieved using a unique identifier, much like words in a dictionary. The magic, however, isn't just in its in-memory nature, but in the variety and intelligence of the values it can store. Unlike simple key-value stores that only handle basic strings, Redis supports a rich set of diverse data structures. This isn't merely a feature. It's a fundamental design decision that allows Redis to be used for a myriad of purposes far beyond simple caching. We're talking about structures like lists, sets, sorted sets, hashes, and even more advanced ones like streams and geospatial indexes, each optimized for specific operations. One of the most remarkable aspects of Redis, contributing significantly to its legendary speed, is its single-threaded nature for handling commands. This means Redis processes one command at a time, preventing race conditions and ensuring atomicity for most operations. While this might sound like a bottleneck, Redis is highly optimized to execute these commands extremely quickly, often measured in microseconds, allowing it to serve tens of thousands or even hundreds of thousands of operations per second on a single core. Long-running operations are carefully managed, and network input-output is handled asynchronously in the background to ensure the command processing thread remains unblocked. 1.2 The Evolution of Redis. A brief history. Redis's story begins in 2009 with Italian developer Salvatore Sanfilippo, better known as Antirez. Originally, he was working on a project that required a real-time analytics system. He found existing database solutions either too complex or too slow for his specific needs, especially for handling real-time data efficiently. Frustrated by the lack of a suitable tool, and with an uncanny knack for elegant software design, Salvatore decided to build his own. The initial versions of Redis focused on solving practical problems that revolved around the set and get functions for strings, and crucially, LPUSH and LPOP for lists, the latter being critical for his analytics needs. The name, Redis itself, is a portmanteau for a remote dictionary server, perfectly encapsulating its core function. What started as a niche tool quickly gained traction among developers. Its simplicity, speed, and the power of its native data structures resonated deeply with the burgeoning needs of web-scale applications. Over the years, Redis has grown organically, adding new data structures, persistence options, replication capabilities, and advanced clustering, all while maintaining its core philosophy of simplicity and performance. Salvatore's meticulous attention to detail and his commitment to robust, efficient code have shaped Redis into the industry giant it is today. In 2020, he famously stepped down from his role as the lead maintainer, passing the torch to the Redis Labs team and the vibrant open-source community, ensuring its continued evolution. 1.3 Key features and differentiators. While Redis is versatile, several key features make it stand out from other data stores. Blazing speed and low latency. This is Redis's hallmark. Because it primarily operates in memory and is optimized for low-latency network communication, it can respond to client requests in mere microseconds. This makes it ideal for use cases demanding immediate data access. Rich data structures. As mentioned, this is a core differentiator. It's not just a fancy feature, it's how Redis provides solutions to complex problems with simple commands. Instead of retrieving raw data and processing it in your application, Redis often allows you to perform operations directly on the data structures in a highly optimized manner. Persistence, RDB, and AOF. Despite being an in-memory database, Redis offers mechanisms to save data to disk, ensuring data durability even if the server crashes or restarts. You can choose from RDB, Redis database, which creates point-in-time snapshots of your dataset, or AOF, append-only file, which logs every write operation. Each method offers different trade-offs between performance and data safety, which we will explore in detail. Replication and high availability. Redis allows you to create multiple replicas, copies of your master instance. This not only provides data redundancy and fault tolerance, but also enables read scaling by distributing read requests across multiple servers. For automatic failover and high availability, Redis Sentinel monitors your instances and promotes a replica to master if the primary one fails. PubSub, Publish Subscribe, Transactions, and Lua scripting. PubSub enables real-time message broadcasting, where publishers send messages to channels and subscribers receive them, facilitating decoupled communication. Transactions allows you to execute a group of commands atomically. They either all succeed or none do, preventing partial updates. Lua scripting offers the ability to execute complex, multi-command logic atomically directly on the Redis server. This reduces network round trips and ensures consistency for sophisticated operations. Extendability with modules. Since Redis 4.0, a powerful module API has allowed developers to extend Redis's functionality with new data types and commands. This has led to the creation of advanced modules like Redis Search, Full Text Search, Redis JSON, JSON Document Store, Redis Graph Database, and Redis Time Series, transforming Redis into a multi-model database capable of handling specialized workloads. 1.4 Common use cases for Redis. Redis's versatility means it's found its way into a vast array of common application patterns. Caching. This is arguably the most prevalent use case. By storing frequently accessed data from slower databases, like relational databases, in Redis, applications can significantly reduce latency and database load. Think of product catalogs, user profiles, or recently viewed items, all perfect candidates for caching. Real-time analytics and leaderboards. Redis's sorted sets are perfect for building dynamic leaderboards for games or real-time ranking systems. Its atomic increment operations, INCR, make it ideal for rapidly updating counters, e.g., website views, likes. Probabilistic data structures like hyperlog enable counting unique items at scale, e.g., unique visitors. Messaging queues and pub subsystems. Redis lists can serve as simple, fast message queues. For more robust and persistent messaging, Redis streams provide a powerful, append-only log tailored for event sourcing and inter-service communication. PubSub is excellent for fan-out scenarios like real-time chat, notifications, or broadcasting system events. Session management. Storing user session data, like login status, Chinese letter contents, or personalized settings, in Redis allows applications to be stateless and scale horizontally, as any server instance can retrieve the user's session from the shared Redis store. Distributed locks and rate limiting. In distributed systems, ensuring that only one process accesses a shared resource at a time is crucial. Redis can be used to implement highly available distributed locks. Similarly, its fast counters and expiry capabilities make it an excellent choice for enforcing API rate limits. Geospatial indexing. For applications that deal with location data, e.g., find nearby restaurants, ride-sharing services, Redis's geospatial commands allow efficient storage of latitude-longitude coordinates and powerful radius-based queries. These are just a few examples. The creativity of developers continues to push the boundaries of what Redis can accomplish. 1.5. Setting up your Redis environment. Before we dive deeper, let's ensure you have a basic Redis environment set up. While detailed installation instructions vary by operating system, the general process is straightforward. Installation, general steps, Linux, Ubuntu/Debian, sudo apt update, and sudo apt install Redis server. macOS homebrew, brew install Redis. Docker run name myredis, p6379, 6379d Redis. This is highly recommended for quick setup and isolation. Once installed, Redis typically runs as a background service. You can interact with it using the Redis CLI utility provided with the installation. Basic interaction with Redis CLI. Open your terminal and type Redis CLI. You should see a prompt like 127.0.0.1:6379. To test if Redis is running, ping should respond with pong. To set a key value pair, set Mikey hello Redis should respond with OK. To retrieve a value, get Mikey should respond with hello Redis. To exit Redis CLI, quit. For more advanced configuration, the redis.conf file, typically located at /etc/redis/redis.conf on Linux or /usr/local/etc/redis.conf with homebrew, allows you to customize persistence, memory limits, network interfaces, and much more. We'll explore critical settings in later chapters. 1.6 The Journey Ahead, What You'll Learn. This book is structured to guide you from foundational knowledge to advanced topics, always with a focus on practical application. In Part 1, The Foundations of Redis, will solidify your understanding of Redis's core data structures and how to interact with them effectively. Part 2, Performance and Scalability, is where we dissect the engine of Redis. You'll learn how to analyze its performance characteristics, optimize your data models and command usage, and scale Redis across multiple machines using replication, sharding, and clustering. Part 3, Redis Design Patterns, will transform your theoretical knowledge into practical solutions. We'll explore how Redis is used to implement common architectural patterns for caching, real-time analytics, messaging, and distributed systems, providing you with blueprints for your own applications. Finally, Part 4, Best Practices and Advanced Topics, focuses on operational excellence. You'll discover how to secure your Redis deployments, monitor their health, troubleshoot issues, perform routine maintenance, and leverage cutting-edge Redis modules for specialized use cases. We'll conclude with a comprehensive guide to deploying Redis robustly in production environments, whether on-premise, in the cloud, or with Kubernetes. By the end of this journey, you won't just understand Redis commands. You'll understand its philosophy, its strengths, and how to harness its power to build fast, scalable, and resilient applications. Let's begin. Chapter 2, Redis Data Structures in Depth. Chapter 1 introduced Redis as an in-memory data structure store, highlighting its speed and versatility. This chapter is where we truly unpack that versatility by diving deep into the core data structures that make Redis so powerful. Understanding these structures isn't just about knowing their commands. It's about grasping their underlying behavior, their optimal use cases, and the performance implications of choosing one over another. Each structure is a specialized tool designed to solve a particular class of problems efficiently. Mastering them is key to truly mastering Redis. 2.1 Strings, the simplest powerhouse. At its most fundamental, Redis is a key value store, and strings are the most basic type of value you can store. A Redis string can hold any kind of data: a piece of text, a JSON object, a serialized object, or even binary data like an image. Despite their simplicity, Redis strings offer a surprisingly rich set of operations beyond mere setting and getting. Concepts: basic key value pairs. Each key maps to a single string value. Binary safety. Strings are treated as binary safe byte arrays. This means you can store anything from text, encoded in UTF-8, ASCII, etc., to raw images or serialized application objects. Redis doesn't interpret the content, only stores and retrieves it. Maximum size. A Redis string can be up to 512 megabytes in size. While possible, storing very large strings might not always be the most performant or memory-efficient approach, and we'll discuss memory management and its implications in Chapter 4. Key commands, set and get. These are the most common commands for storing and retrieving a string value associated with a key. When you set a key, if it already holds a value, the old one is replaced atomically. Del and EXISTS. You can delete a key entirely or simply check if a key exists in the database. Expire and TTL. These are fundamental for temporary data like caches. Expire sets a time limit, in seconds, after which a key will automatically be removed. TTL allows you to check how much time is left before expiration. INCR, DECR, INCRBY, DECRBY. These commands are used for atomic increments and decrements. If a key contains a string that represents an integer, you can atomically add to or subtract from it. This is invaluable, for example, for managing counters in a high concurrency environment. Append. This command allows you to add a string to the end of an existing string value. If the key doesn't exist, it's created first. GETRANGE and SETBIT, GETBIT. You can retrieve portions of a string or manipulate individual bits within a string. This effectively allows a Redis string to be used as a bitmap, which is incredibly efficient for certain use cases. Use cases for strings, caching website content. Scenario: storing frequently accessed HTML pages or JSON responses from API endpoints to reduce the load on your primary database. Application: when a request for specific product details comes in, your application first checks Redis using the GET command on a key like product 123 details. If found, it's a fast cache hit. Otherwise, the application fetches the data from a slower database, then uses set to store it in Redis, often with an expire time, so it's fresh for subsequent requests. Counters. Scenario: rapidly and accurately counting events, such as web page views, likes on a social media post, or the number of items remaining in inventory. Application: commands like INCR, page, home, views, or INCRBY, user, 101, posts. 5 allow multiple clients to update a counter simultaneously without risk of race conditions, ensuring a precise count even under heavy load. Session tokens/authentication. Scenario: managing user login sessions in a distributed web application. Application: after a user logs in, a unique session token can be stored as a Redis string, mapping the token to the user's ID using a command like set session upxis user 54321 x 86400. The expire property ensures sessions automatically terminate after a set period, improving security and managing memory. Bitmaps for user presence or activity. Scenario: efficiently tracking the daily presence of millions of users, for example, to determine daily active users. Application: you can use a single Redis string to represent a specific day. Each bit in that string corresponds to a user ID. To mark user ID 101 as active on January 1st, 2024, you'd use SETBIT, daily active users, 2024 to 1 101. Later, you can check activity using GETBIT or count all active users for that day with the bitcount command. This is incredibly memory efficient for large, sparse datasets. Strings, despite their apparent simplicity, are the workhorses of many Redis applications. Their directness and the optimized atomic operations they offer make them invaluable for numerous performance-critical tasks. 2.2 hashes, representing objects efficiently. Think of Redis hashes as objects or records. They are perfect for representing structured data where you have several fields. For example, a user profile might have fields like name, email, age, and last login. Storing these as individual strings would result in many keys, e.g., user, one name, user, one email, which can be less efficient. A hash allows you to store all these fields under a single logical key. Concepts: field value pairs under a single key. A hash is a collection of field value pairs that are stored within a single Redis key. Both the field and its value are strings. Memory efficiency. For objects with many fields, hashes can be more memory efficient than storing each field as a separate string, especially when Redis can optimize their internal storage for smaller hashes. Key commands: HSET. This command allows you to set the value of a specific field within a hash. You can set a single field or multiple field value pairs in one go. HGET and HMGT. Use HGET to retrieve the value of a single field. HMGT lets you fetch multiple field values from a hash in a single operation, reducing network round trips. HGETALL. This command retrieves all fields and their values from a hash. Be cautious using this command on very large hashes, as it can consume significant network bandwidth and potentially block the Redis server while processing. For large collections, an iterative scanning approach using HSCAN, discussed in Chapter 5, is often much more appropriate. HINCRBY. Similar to string increments, HINCRBY atomically increments the integer value of a numeric field within a hash. HDEL, used to delete one or more fields from a hash. HLEN, HKEYS, HVALS, HEXISDS. These commands allow you to get the number of fields in a hash, list all its field names, list all its values, or check if a specific field exists within a hash, respectively. Use cases for hashes: storing user profiles or product catalogs. Scenario: each user or product in your system has many attributes that are often accessed together. Application: you can store all attributes of user 101 within a single hash using HSET user 101, name Alice, email alice@example.com, age 30, last login 2024 to 1 to 0 1 T1000Z. To retrieve Alice's email, you use HGET user 101 email. If you need all her details for a profile page, HGTAL user 101 is efficient for hashes of moderate size. Representing shopping cart contents. Scenario: a user's shopping cart contains multiple items and you need to track the quantity of each. Application: a hash key like cart user 202 can represent a user's cart. Product IDs are fields and their quantities are values. Adding items or updating quantities is simple and atomic. HINCRBY cart user 202 product A1. Counters with multiple dimensions. Scenario: you need to track views for a page, but also want to break down those views by browser type. Application: instead of many separate string counters, a single hash key page home views browser can have fields for Chrome, Firefox, Safari, etc., storing their respective counts. Each view would trigger HINCRBY, page, home, views, browser. Chrome, 1 hashes are incredibly useful for structured, object-like data, providing both memory efficiency and the ability to retrieve or modify specific attributes without fetching the entire object. 2.3 lists, ordered collections with versatility. Redis lists are essentially sequences of strings. Unlike arrays, adding elements to a Redis list is always fast, regardless of the list's length, because it's a constant time operation, O1, at the head or tail. This makes them ideal for scenarios where you are primarily adding or removing items from the ends of the collection. Accessing elements by index, e.g., using lindex, is slower, as Redis has to traverse the list, on. Concepts: ordered insertion. Elements are kept in the order they are inserted, or the order in which they are specified for insertion. FIFO-LIFO operations. Lists are perfect for implementing queues, first in, first out, where elements are added to one end and removed from the other, or stacks, last in, first out, where elements are added and removed from the same end. Blocking operations. Redis lists support powerful BLPOP and BRPOP commands. These allow a client to wait for an element to appear in a list. If the list is empty, the client connection blocks until a new element is pushed or a specified timeout is reached. This is a fundamental building block for highly efficient worker queues. Key commands: LPUSH and RPUSH, used to insert elements at the head, left L or tail, right R of a list, respectively. You can push multiple values in a single command. LPOP and RPOP, used to remove and return elements from the head, left L or tail, right R of a list. These are crucial for queue processing. LRANG, retrieves a range of elements from a list, specified by start and stop indices. This is useful for fetching recent items or paging through a list. LLEN returns the number of elements in a list. BLPOP and BRPOP. These are the blocking variants of LPOP and RPOP. They are designed for reliable message queuing patterns, waiting for data if the queue is empty. LINDEX retrieves an element from a list by its zero-based index. Use this cautiously for very long lists due to its O(n) complexity. LREM removes specific occurrences of a value from a list. Use cases for lists: message queues, worker queues, scenario. A common architectural pattern where a web application needs to offload computationally expensive or time-consuming tasks, e.g., image resizing, sending emails, generating complex reports, to background workers. Application. When a user triggers such a task, the web application uses LPUSH to add a task ID or message onto a Redis list, e.g., image processing queue. A background worker constantly uses BLPOP on this queue. When a new task appears, BLPOP retrieves it, the worker processes it, and then signals completion. This decouples parts of your system, improving responsiveness and fault tolerance. Chronologies/timelines, scenario. Storing a chronological feed of events, such as the latest blog posts, social media updates, or a user's recent activities. Application. Each new event is added to the head of a list using LPUSH user 123 activitalog activityd-n. To display the 10 most recent activities, you can simply use LRANGA user 123 activitalog 09. Lists also allow easy management of bounded collections, e.g., keeping only the 50 most recent items using the LTRIM command. Implementing stacks, LIFO, scenario, any situation where you need a last-in, first-out data structure, like managing undo-redo operations. Application. Using LPUSH to add elements, the push operation, and LPOP to remove them, the pop operation perfectly simulates a stack. Lists are extremely versatile for ordered collections, especially when dealing with elements at the ends of the collection or when building producer-consumer patterns. 2.4 sets, unique and unordered collections. Redis sets are collections of unique strings. Unlike lists, the order of elements in a set is not preserved, and each element can only appear once. If you attempt to add an element that is already present, the command is simply ignored. This feature makes sets ideal for situations where you need to store and retrieve unique items and perform operations familiar from set theory, like unions, intersections, and differences between multiple sets. Concepts, unique string members. Every element added to a set must be unique. This property is enforced by Redis. Unordered. The order in which elements are stored or retrieved from a set is not guaranteed. Efficient membership testing. Checking if an element exists in a set using the SISMEMBER command is an extremely fast O(1) operation, making it ideal for quick lookups. Key commands, SADD, adds one or more members to a set. SMEMBRS returns all members of a set. Similar to HGTLL, use this with caution on very large sets as it can be resource-intensive. For large sets, SSCAN, covered in Chapter 5, is the preferred iterative approach. SISMEMBR checks if a specific member is present in a set, returning a Boolean-like result. SBOP removes and returns one or more random members from a set. SREM removes specified members from a set. SCARD returns the number of members cardinality in a set. SINTER, SUNION, SDIFF. These powerful commands perform set algebraic operations. SINTER finds common members across multiple sets, intersection. SUNION combines all members from multiple sets, union. SDIFF finds members present in the first set, but not in any of the subsequent sets, difference. Use cases for sets, tracking unique visitors, scenario. You want to count the exact number of unique users who visited a specific web page or your entire site on a given day, week, or month. Application. For each user visit, you add their user ID to a Redis set using SADD uniquevisitors, 2024 to 1:1, user ID X. Since SADD automatically handles duplicates, if the same user visits multiple times, their ID is only stored once. At any time, SCARD unique visitors, 2024 to 1 gives you the precise count of unique visitors. User tagging/categorization. Scenario: storing tags associated with an article or defining interest categories for users. Application: an article might have SADD article 123 tags, tech, coding, databases. You could then find articles that share common tags using Sinter. Access control lists, ACLS permissions. Scenario: defining groups of users who have specific permissions or roles, e.g., admin users, moderators. Application: SADD administrators. User 123, user 456. To quickly check if user 789 is an administrator, you use SISMEMBER administrators. User 789. Social graph applications, friend lists followers. Scenario: representing who is friends with whom or who follows whom on a social network. Application: SADD friends user 1, user 2, user 3 records that user 1 is friends with user 2 and user 3. Finding common friends between user 1 and user 2 becomes a simple Sinter, friends, user 1, friends, user 2 operation. Sets are incredibly powerful for managing unique collections, providing fast membership testing and set algebraic operations that are typically very complex and slow in traditional databases. 2.5 Sorted sets. Sorted collections with scores. Redis sorted sets are unique hybrid data structures. Like regular sets, they contain unique, non-repeating string members. However, the defining feature of a sorted set is that each member is associated with a numerical score. This score is what determines the order. Elements are always stored ordered by their scores, from the lowest score to the highest. If elements have the same score, they are ordered lexicographically, alphabetically, to ensure a deterministic order. Concepts: unique members with scores. Each member is unique, but it holds a corresponding floating point number score. This score can be any valid double precision floating point number. Sorted by score, elements are automatically maintained in sorted order based on their scores. Efficient range queries. You can quickly retrieve elements within a specific score range, e.g., all members with scores between 100 and 200, or by rank, their position in the sorted list, e.g., the top 10 members. Key commands: ZADD adds one or more members with their scores to the sorted set. If a member already exists, its score is updated, and its position in the set adjusts accordingly. ZRANGE and ZREVRANGE. These commands allow you to retrieve elements by their rank, position, in the sorted set. ZRANGE gives you elements from lowest to highest score, while ZREVRANGE retrieves them from highest to lowest. You can specify whether to include the scores in the result. ZRANK and ZREVRANK. These commands return the rank, zero-based index, of a specific member in the sorted set, useful for finding someone standing in a leaderboard. ZSCORE retrieves the score of a specific member. ZINCRBY atomically increments the score of a member by a specified amount. This is perfect for, say, updating a player's score on a leaderboard. ZREM removes one or more members from the sorted set. ZCARD returns the number of members in a sorted set. ZRANGBYSCORE. This command is highly powerful, allowing you to retrieve all elements within a specific score range, regardless of their rank. You can also apply limits to these queries to fetch, for example, just the first 5 elements within that range. Use cases for sorted sets, leaderboards, scenario. Building high-score tables for games, ranking users based on points, or displaying the top-end performers in any system. Application. When a player scores points, you update their score in the leaderboard with ZADD game, leaderboard, newscore, player, Charlie. Then, to display the top 10 players, you simply use ZREVRANG, game, leaderboard, 09WITHSCORES. Redis automatically keeps the list sorted, making these operations very fast. Ranking systems, scenario. Ranking products by popularity, articles by votes, or users by overall reputation. Application. You can create a product, popularity, sorted set where the score is the number of sales or upvotes. As a product gains votes, its score is updated, and its rank changes dynamically. Elements with priorities. Scenario: managing a task queue where tasks have different priorities or elements needing to be processed in a specific order based on a numerical value. Application: you can ZADD priority tasks 1 task low priority and ZADD priority tasks 10 task high priority. To get the highest priority task, you'd use ZRANG priority tasks 00. Time series data simple aggregation. Scenario: while the Redis time series module, discussed in Chapter 12, is often better for complex time series, sorted sets can handle simple time-based events. Application: store events where the score is a Unix timestamp and the member is the event data. You can then query for events within a specific time range using ZRANG-BYSCORI. Sorted sets are indispensable wherever ordered collections with associated scores are needed, providing powerful ranking and range query capabilities unmatched by other simple data structures. 2.6 Redis Streams. Event sourcing and messaging. Introduced in Redis 5.0, streams are a powerful, append-only data structure that can revolutionize how you handle event logging, messaging, and inter-service communication. They are conceptually similar to external message brokers like Apache Kafka or AWS Kinesis, providing a persistent, ordered, and replayable log of events, but with the simplicity and performance Redis is known for. Concepts: append-only log. New entries, messages, or events are always added to the very end of the stream. Events are never deleted from the middle, ensuring a complete history. Unique IDs. Each entry in a stream receives a unique, automatically generated ID. This ID is typically a combination of a timestamp, milliseconds from Unix epoch, and a sequence number, e.g., 1,678,886,400,000 to 0, guaranteeing uniqueness and natural ordering. Consumer groups. Streams support sophisticated consumer groups. A consumer group allows multiple, independent consumers or applications to process the same stream concurrently. Redis manages which consumer receives which messages within a group and tracks message acknowledgement, ensuring efficient and reliable processing across a distributed set of workers. Key commands: illustrative, not exhaustive. XADD. The primary command to append a new entry to a stream. You specify the stream key and an ID, usually for auto-generation, followed by field value pairs for the entry's content. XRANG retrieves a range of entries from the stream based on their IDs or timestamps, allowing you to fetch historical data or segments of the log. XREAD, used by clients to read entries from one or more streams. It can block until new messages are available, making it suitable for real-time processing. XGROUP create. This command is used to set up a new consumer group for a stream. You specify the stream key, the group name, and the ID from which this group should start reading messages. XREADGROUP. Consumers within a consumer group use this to read messages. Redis ensures that each message is delivered to only one consumer within that specific group. XACK. Consumers use this command to acknowledge that they have successfully processed a message. This is vital for ensuring message delivery guarantees and managing pending messages. XBENDING and XCLAIM. These commands are used to inspect and manage messages that have been delivered to a consumer in a group, but not yet acknowledged. XCLAIM allows another consumer to take ownership of processing messages that appear to be stuck. Use cases for streams: event sourcing. Scenario: architectures where every significant state change in an application is captured and stored as an immutable event, providing a complete historical record. Application: a user's shopping cart state changes, e.g., item added, quantity updated, checkout initiated, can each be appended as discrete events to a stream like cart events, userid. This provides a reliable audit trail and allows for the easy reconstruction of the cart's state at any point in time. Persistent message queues. Scenario: building robust, scalable message queues with features like guaranteed delivery, multiple consumers, and message reprocessing on failure. Application: different services can publish tasks to a stream like microservice tasks. Dedicated workers, organized into a consumer group, can then read messages using XREADGROUP, ensuring each task is processed by only one worker within that group. If a worker fails before acknowledging a message, the message remains pending and can be reprocessed by another worker. Real-time data ingestion. Scenario: collecting log data, sensor readings from IoT devices, or real-time user activity data. Application: devices XADD their readings to a sensor data stream. Backend analytics services or dashboards can then XREAD from the stream to process data as it arrives, enabling immediate insights and reactions. Replication between services, change data capture, CDC. Scenario: one service publishes changes, e.g., database updates, to its internal data model to a stream. Other services can then subscribe to this stream to receive and react to these changes, maintaining data consistency and propagating updates across a microservices architecture without direct coupling. Streams are a more advanced data type, providing significantly more power and flexibility for messaging and event-driven architectures compared to simple lists or the pub/sub model. They are ideal for systems that demand high message throughput, robust delivery guarantees, at least once processing with consumer groups, and historical access to event data. 2.7 Geospatial indexes. Location-based data. Redis provides native support for managing geospatial data, allowing you to store latitude and longitude pairs and perform efficient radius-based queries. This capability is built upon the sorted set data structure, cleverly leveraging the geohash encoding strategy. Concepts: geohash encoding. Latitude and longitude coordinates are converted into a single string, geohash. A key property of geohashes is that locations that are close to each other on Earth will have very similar geohash strings, especially at the beginning of the string. Sorted set implementation. Redis stores these geohashes as members in a sorted set, with their numerical geohash representation used as the score. This clever trick allows Redis to use the optimized range query capabilities of sorted sets for efficient geographic lookups. Earth as a sphere. Underlying calculations for distances and radii are performed using a spherical model of the Earth for accuracy. Key commands: GEOADD. This command is used to add one or more members, e.g., location names like Eiffel Tower or Coffee Shop A, along with their longitude and latitude to a geospatial index. GEODIST calculates the distance between two members' locations already stored in the same geospatial index. You can specify the unit of measurement, meters, kilometers, feet, or miles. GEORADIUS and GEORADIUSBYMBR. These are the core query commands. GEORADIUS finds members within a specified radius from a central point, defined by its longitude and latitude. GEORADIUSBYMBR performs the same query, but centers it around an existing member within the geospatial index. Both commands allow for additional options, such as returning coordinates, distances, or limiting the number of results. GEOHASH returns the geohash string for one or more specified members. Use cases for geospatial indexes. Find nearby features. Scenario: a fundamental feature in many mobile apps, allowing users to find restaurants, stores, gas stations, or friends within a certain radius of their current location. Application: you would populate a Redis geospatial index with your business locations using GEOADD. When a user requests restaurants nearby, your application uses GEORADIUS with the user's current coordinates to quickly retrieve all relevant businesses within, say, a 5-kilometer radius. This offloads complex geospatial calculations from your application or a larger, potentially slower database. Location-based services, LBS. Scenario: powering ride-sharing applications, finding nearby drivers, dating apps showing nearby matches, or delivery services. Application: drivers' current locations can be continuously updated in a Redis geospatial index. When a passenger requests a ride, the application uses GEORADIUSBYMBR, centered on the passenger's stored location, to identify the closest available drivers, ensuring quick and efficient service. Real-time tracking and proximity alerts. Scenario: tracking moving objects like fleet vehicles or assets and triggering alerts if they enter or leave predefined geographic zones. Application: as vehicle locations are updated, You can run periodic GeoRadius queries against known geofences to detect zone crossings and trigger notifications. Redis's geospatial capabilities offer a lean, fast solution for location-based applications, especially prevalent in mobile and logistics sectors, without requiring a separate, heavy-duty geographic information system, GIS. 2.8 Probabilistic data structures, hyperloglog, Bloom filters. Redis extends its ecosystem beyond exact data structures to include powerful probabilistic data structures. These highly specialized structures offer impressive memory efficiency and speed for certain types of queries, often at the cost of a small, configurable margin of error. They are indispensable for applications where approximate answers are acceptable, but exact calculations would be too resource-intensive or computationally prohibitive. 1 Hyperlog HLL. Counting unique items approximately. Concepts: cardinality estimation. Hyperlog is an algorithm used to estimate the number of unique elements in a set, its cardinality. Fixed memory footprint. This is its most striking feature. Regardless of how many unique items you add, a hyperlog always uses a very small, fixed amount of memory, approximately 12 KB. This makes it incredibly scalable for massive datasets. Small error rate. The estimate produced by hyperlog has a very low standard error, typically around 0.81%, making it highly accurate for most analytical purposes. Key commands: pfadd adds one or more elements to a hyperlog. If an element is already present, it is simply ignored as Redis tracks uniqueness. pfcount returns the approximated cardinality of one or more hyperlog. This is the unique count you are looking for. pfmerge merges multiple hyperlog into a single one. This is useful for combining daily unique counts into weekly or monthly totals. Use cases for hyperlog. Unique visitor counts. Scenario: a website or mobile application needs to track the number of unique users who visited a page, an entire site, or performed a specific action on a given day, week, month, or overall. Doing this with traditional sets would consume enormous amounts of memory for a popular site. Application: for each user visit, you pfadd their user id to a hyperlog key for that day, like dale uniques, 24 to 1 to 1. Then, pfcount dale uniques, 24 to 1 to 1, gives you a very accurate estimate of unique visitors. pfmerge can combine these daily counts into weekly uniques or monthly uniques without reprocessing raw data. Benefit: extremely memory efficient for very high traffic sites with millions or billions of unique events, where an exact count using traditional sets would be prohibitive. Counting unique searches. Tracking the number of unique search terms used on a platform without storing all the terms. 2 Bloom filters. While not a data type native to the core Redis distribution, Bloom filters are a popular probabilistic structure commonly used with Redis through the Redis Bloom module, which needs to be loaded separately. They address a fundamental set membership problem. Concepts: probabilistic membership testing. A Bloom filter can tell you if an element might be in a set with a configurable false positive rate or definitely is not. It can never produce a false negative, claiming an element isn't in the set when it actually is. Fixed size. Like hyperlog, its memory footprint is determined by the expected number of items and the acceptable false positive rate, not the actual number of items added. This makes it very space efficient. No deletion. Elements cannot be reliably removed from a standard Bloom filter, as removing one might inadvertently affect the present status of other, unrelated elements. Key commands from Redis Bloom module: bfadd adds an item to the Bloom filter. bfexists checks if an item might exist in the Bloom filter. Returns 1 for possibly exists, 0 for does not exist. bf.info provides information about the Bloom filter's configuration and current state. Use cases for Bloom filters: fast element exists, checks e.g. deduplication. Scenario: preventing duplicate user signups, check if an email already exists, or efficiently deduplicating events in a high-volume data stream. Application: before inserting a new email into a database, you first bfadd register emails, newser@example.com. Then, for subsequent signups, you use bfexisds, register emails, potential duplicate at example.com. If the filter says does not exist, you know for certain it's a new email. If it says possibly exists, you then perform a slower, exact check against your primary database. Benefit: avoids costly database lookups for every exists check, especially beneficial when most queries are for items that do not exist. Caching negative lookups: remembering keys that are not asterisk present in a primary data store to avoid repeated expensive lookups. Probabilistic data structures are powerful tools for specific analytical challenges, offering a trade-off of slight inaccuracy for massive gains in efficiency. They highlight Redis's capability to handle large-scale data problems creatively. Chapter 3: Connecting and Interacting with Redis. In the previous chapter, we delved into the rich tapestry of Redis's native data structures, understanding their individual strengths and typical applications. Knowing what Redis can store is one thing, understanding how to effectively communicate with it and leverage its operational paradigms is another. This chapter bridges that gap, exploring the client-server model, essential command line interactions, fundamental concepts of atomicity, the mechanics of transactions, real-time messaging, and even server-side scripting. 3.1 Understanding Redis client-server model. Redis operates on a classic client-server model. Your application, the client, connects to a running Redis instance, the server, over a network, typically using a standard TCP/IP socket. Once connected, the client sends commands to the server, and the server processes these commands and sends back responses. The communication protocol is relatively simple and efficient. The client sends a command as a sequence of bytes, and the server replies with a specific data type, e.g., a simple string, an integer reply, a bulk string for binary data, or an array of strings. This streamlined request-response protocol is one of the reasons for Redis's low latency. For most applications, direct raw TCP socket programming is cumbersome. Therefore, developers use Redis client libraries available for virtually every popular programming language, e.g., Jedis for Java, Stack Exchange Redis for C, RedisPy for Python, Node-REDIS for Node.js. These libraries abstract away the low-level network details, providing a convenient and idiomatic way to interact with Redis from your chosen language. Client libraries also manage connection pooling. Instead of opening and closing a new TCP connection for every command, connection pooling maintains a set of ready-to-use connections. When your application needs to send a command, it borrows a connection from the pool, uses it, and then returns it to the pool. This significantly reduces the overhead associated with establishing new connections, which is crucial for high-performance applications. Without proper connection pooling, the time spent setting up and tearing down network connections can easily outweigh the actual command execution time within Redis itself. 3.2 Essential Redis CLI commands. While your applications will use client libraries, the Redis CLI Redis command line interface is an indispensable tool for development, debugging, and administration. It allows direct interaction with a Redis instance. You've already seen set and get, but let's cover some more fundamental Redis CLI commands. Server introspection, ping. A simple command to check if the Redis server is alive and responding. It returns pong. Info section provides a wealth of information about the Redis server, its memory usage, client connections, persistent status, replication, and performance statistics. You can request specific sections, e.g., info memory, info clients. This command is vital for monitoring and troubleshooting, which we'll explore in detail in Chapter 11. DBSIZ returns the number of keys in the currently selected database. LASDSAVE returns the Unix timestamp of the last successful save of the dataset to disk. FLUSHDB clears all keys from the currently selected database. FLUSHALL clears all keys from all databases on the Redis server. Use these flush commands with extreme caution in production environments as they irrevocably delete data. Key management, keys pattern, finds all keys matching a given pattern, e.g., keys user, to find all keys starting with user. Warning, this command iterates over all keys in the database. In a production environment with a large number of keys, keys can block the server for a significant time, impacting performance. It should never be used in production for routine operations. For pattern-based iteration over keys in a non-blocking manner, the scan command is always preferred and will be discussed in Chapter 5. Del key deletes one or more specified keys. Exisds key checks if one or more keys exist. Expire key seconds sets a timeout on a key, as seen in Chapter 2. After the specified number of seconds, the key is automatically deleted. TTL key returns the remaining time to live in seconds of a key with an expiry set. Persist key removes the expiration from a key, making it persistent. Type key returns the data type of the value stored at key, e.g., string, hash, list, set, zet. These commands help you manage your Redis data and inspect the server's state, forming the foundation of effective interaction. 3.3 Data serialization and deserialization. When you store application-specific data in Redis, such as complex objects, lists of objects, or deeply nested JSON, Redis treats these values simply as binary safe strings. It has no inherent understanding of the structure or meaning of the data within these strings. This means that your application is responsible for serializing the data into a format that Redis can store a string of bytes before sending it, and then deserializing it back into a usable object when retrieving it. Choosing the right serialization format is important and depends on your application's needs. Plain text strings, simple, human-readable, and suitable for basic values. JSON, JavaScript Object Notation. Very popular due to its human readability, widespread language support, and flexibility. It works well for structured data. Message pack, a binary serialization format that is more compact and faster to parse than JSON, but not human-readable. Protocol buffers, Protobuf, or Apache Avro, schema-driven binary formats that offer strong type checking, very high performance, and extreme compactness. They require defining a schema upfront. Considerations for choosing a serialization strategy. Performance. How fast can your application serialize and deserialize data? Binary formats are generally faster than text-based ones. Memory footprint. How much space does the serialized data consume in Redis? Compact formats save memory, which directly impacts your Redis instance's capacity and cost. Interoperability. Do different services, potentially written in different languages, need to read and write the same data? Standardized formats like JSON or Protobuf excel here. Human readability debugging. Can you easily inspect the data in Redis using Redis CLI? Plain text and JSON are better for debugging. Redis itself performs no serialization or deserialization beyond storing and retrieving the byte array you give it. This responsibility squarely rests with the client application. Effective serialization is crucial for both performance, as it minimizes data transfer size, and memory efficiency within Redis. 3.4 Atomic operations. The cornerstone of consistency, a core design principle that underpins Redis's reliability and consistency, is the atomicity of its operations. Atomicity means that an operation is treated as a single, indivisible unit of work. It either completes entirely and successfully, or it fails completely, leaving the system's state unchanged. There is no in-between partially completed state. As discussed in Chapter 1, Redis is inherently single-threaded for command execution. This design choice is fundamental to its performance and consistency guarantees. Because only one command is processed at a time, there are no race conditions at the server level for single commands. If multiple clients send commands simultaneously, Redis queues them and processes them sequentially. This means that any single Redis command is inherently atomic. For example, when you INCR a counter, nothing else can happen to that counter until the INCR operation is fully completed. You don't need to worry about two clients trying to increment the same counter at the exact same millisecond, resulting in a lost update. Redis guarantees that the counter will be correctly incremented by both operations. This strong guarantee for single commands makes building concurrent applications significantly simpler, as you don't need external application-level locks for simple operations. However, real-world scenarios often require performing multiple commands as a single atomic unit. This is where Redis transactions and Lua scripting come into play. 3.5 Transactions. MULTI, exec discard. Redis transactions provide a way to execute a group of commands as a single, atomic operation. The process involves queuing commands and then executing them all at once. The commands used are MULTI. This command marks the beginning of a transaction block. Any subsequent commands issued by the client are not executed immediately, but are instead queued up. Exec. This command triggers the execution of all commands that were queued since the MULTI command. If the transaction completes successfully, all queued commands are executed sequentially. Discard. If you decide you don't want to execute the queued commands, discard will clear the transaction queue and abort the transaction. Let's consider a practical scenario for a simple transaction: transferring points between two users. Imagine you want to transfer 10 points from user Alice points to user Bob points. This involves 3 conceptual steps: decrement Alice's points, increment Bob's points, check if Alice had enough points before the transfer. Without a transaction, if you performed these as separate commands, it's possible for another process to modify Alice's points between your DECR and INCR operations, leading to an inconsistent state. With a transaction, you'd queue them. MULTI, DCRBY user Alice, points 10. INCRBY user, Bob, points 10. Exec. All these operations are guaranteed to be executed atomically in the order they were queued. Optimistic locking with watch. Redis transactions also support a form of optimistic locking using the watch command. Watch allows you to monitor one or more keys before starting a transaction. If any of the watched keys are modified by another client during the MULTI exec block, the transaction will be canceled and will not execute. This provides a way to implement, check, and set patterns safely. For example, to implement the points transfer safely, ensuring Alice actually has enough points at the moment of transfer. Watch user Alice points. Get user Alice points. Application logic checks if points equals 10. MULTI. DCRBY user Alice points 10. INCRBY user Bob points 10. Exec. If after the watch but before exec, another client changes user Alice points, the exec command will return nil, indicating the transaction failed. Your application then needs to retry the operation. Limitations of Redis transactions. It's important to understand that Redis transactions are not full-fledged ACID, atomicity, consistency, isolation, durability transactions in the relational database sense. No rollbacks on command failure. If a command within a MULTI block fails due to a semantic error, e.g., trying to perform a list operation on a string key, Redis will still execute the other commands in the transaction. It will not roll back the commands that succeeded earlier in the transaction. This differs from many traditional relational databases. Queuing, not execution, commands are queued and then executed. They are not checked for validity until exec is called. Despite these differences from traditional database transactions, Redis transactions, especially when combined with watch, are extremely valuable for ensuring consistency and atomicity for multi-command operations. 3.6 Publish-Subscribe, PubSub. Redis provides a lightweight and efficient implementation of the Publish-Subscribe, PubSub, messaging paradigm. This pattern allows different parts of your application, or even entirely separate applications, to communicate in a decoupled manner. The core components of PubSub are publishers, clients that send messages; subscribers, clients that receive messages; channels, named message queues through which publishers send messages and subscribers receive them. Publishers don't know who is subscribing, and subscribers don't know who is publishing. This decoupling is a major benefit. Key commands: publish channel message, sends message to the specified channel. Any client currently subscribed to that channel will receive the message. Subscribe channel. A client dedicates its connection to listen for messages on one or more specified channels. Once in subscribe mode, this connection cannot be used for other Redis commands until it unsubscribes. PSUBSCRIB pattern allows a client to subscribe to channels that match a specific pattern, e.g., PSUBSCRIB news, would subscribe to news sports, news tech, etc. Use cases for PubSub, real-time updates, broadcasting live scores, stock price updates, or sensor data readings to connected clients. Chat applications, a classic use case where users subscribe to chat rooms, channels, and send messages publish. Event notifications, notifying various microservices about an event, e.g., user profile updated, without direct coupling. Limitations of PubSub. It's crucial to understand that Redis PubSub offers a fire-and-forget messaging model. No persistence. If a subscriber is not connected when a message is published, they will not receive that message. Redis does not store messages for offline subscribers. No delivery guarantees. There's no built-in mechanism to ensure a message was successfully processed by a subscriber. Order not strictly guaranteed across connections. While messages within a single publish command are ordered, if you have multiple publishers sending to the same channel, their messages might arrive at subscribers in a slightly different order due to network latency. For scenarios requiring message persistence, delivery guarantees, or the ability to process messages as part of a consumer group, where multiple workers share a queue, Redis streams, discussed in Chapter 2, are a superior and more robust choice. PubSub remains excellent for simple, real-time broadcasts where message loss is acceptable or handled at the application level. 3.7 Executing server-side scripts with Lua. While Redis's single commands are atomic, and transactions can group commands, Lua scripting offers an even more powerful way to execute complex logic atomically and efficiently directly on the Redis server. All commands within a Lua script execute as a single, atomic unit, meaning no other command or script can run concurrently with a running Lua script. Why use Lua scripting? Atomicity for complex logic provides a way to ensure that a sequence of operations, including conditional logic, is executed entirely and without interruption from other clients. Reduced network overhead. Instead of sending multiple commands across the network, you send a single eval command with the script. This is especially beneficial for high-latency connections. Custom commands. Essentially, Lua scripts allow you to define custom server-side functions that behave just like native Redis commands. Key commands. Eval script numkeys key arg. This command executes the Lua script string. Numkeys specifies how many of the subsequent arguments are key names, and the remaining are arguments. This separation is important for Redis cluster to determine which node owns the affected keys. Evalsha SHA-1 numkeys key arg. For performance, instead of sending the entire script string repeatedly, you can first load a script into Redis, using script load, and then execute it by its SHA-1 hash. This saves bandwidth and allows Redis to quickly look up and execute the preloaded script. Example concept, atomic rate limiter. Consider a common rate limiting scenario. Limit a user to 10 requests per minute. A naive approach might involve: get their current request count, INCR it, expire the key if it's new, check if the count exceeds the limit. This requires multiple network round trips and isn't atomic. With Lua, you can implement this entirely on the server side. Local current requests, Redis.call incr, keys 1. If current requests equals 1, then Redis.call expire, keys 1, argv1. And if current requests ta number argv2, then return rejected. Else, return 1 allowed. And then you'd execute the script. Eval, 1 user 123, recount 6010, where keys 1 is user 123. Recount argv1 is 60 seconds and argv2 is the limit 10. This single atomic operation prevents race conditions and is highly efficient. Debugging Lua scripts. Redis provides a powerful debugging tool for Lua scripts called Redis CLI LDB. It allows you to step through your script, set breakpoints, and inspect variables much like a traditional debugger. Caveats of Lua scripting. Blocking operations. A running Lua script executes entirely before any other commands can be processed. If your script is very long-running or performs many operations on large datasets, it can block the Redis server, impacting the responsiveness for all other clients. Scripts should be kept concise and efficient. No direct access to database. Scripts run in a sandboxed environment. They can only interact with Redis via Redis.call and Redis pcall. Error handling. Errors within Lua scripts are generally returned to the client, but careful script design is needed to ensure robustness. Despite these, Lua scripting is an incredibly powerful feature for advanced Redis use cases, bridging the gap between simple command execution and full-fledged application logic. 3.8 Understanding Redis ACLS, Access Control Lists. Security is paramount for any production system, and Redis is no exception. Historically, Redis relied solely on RequirePass for authentication, a single password that granted full administrative access to anyone who knew it. While simple, this approach lacked granular control and was unsuitable for multi-tenant environments or complex applications needing varied access levels. Enter Redis ACLS, Access Control Lists, introduced in Redis 6.0. ACLs provide a robust and granular security model, allowing you to define distinct users with specific permissions for commands, keys, and pub/sub channels. Key concepts of Redis ACLs. Users. You define individual users in Redis, each with a unique username and authentication method, password, password hash, or no password for unauthenticated access. Rules and permissions. For each user, you specify a set of rules that dictate what they can and cannot do. Command permissions, which Redis commands a user is allowed to execute, e.g., +get, flushall, +@read for all read commands, @admin for all admin commands. Key patterns, which keys a user can access, specified using patterns e.g., ~user, * to allow access to all keys starting with user. Channel patterns, which pub/sub channels a user can subscribe to or publish on. Commands for managing ACLS, typically via Redis CLI once authenticated as an admin user. ACL list displays all defined ACL users and their rules. ACL cat lists command categories and their associated commands. ACL user username. This is the primary command for creating, modifying, and deleting users. ACL setuser username on-off password /nopes plus command ~pattern /+ pattern and channel sets up user rules. On-off, enable or disable the user. Password, sets a plain text password for the user. Use ACL setuser alice hashoff password to set a hashed password for stronger security where the hash is computed externally. Nopes, user requires no password. Plus command, grant deny specific commands. Plus at category, grant deny entire categories of commands, e.g. @read, @write, @admin. Pattern, grant access to keys matching a pattern. Pattern denies access. And channel plus channel, grant deny access to pub/sub channels. ACL save, saves the current ACL configuration to the Redis ACL file configured in redis.conf, ensuring changes persist across restarts. ACL auth username password authenticates the current connection as a specific user. Best practices for Redis ACLs, principle of least privilege, grant only the minimum necessary permissions to each user or application. For example, a caching service might only need get, set, and expire permissions on specific key patterns. Use strong, unique passwords. Avoid using default or easily guessable passwords. Regularly review ACLs. Periodically audit your ACL configurations to ensure they align with your current security requirements. Combine with network security. ACLs are just one layer of defense. They should always be combined with network-level security measures like firewalls, VPNs, or running Redis in a private network, as discussed in Chapter 10. ACLs represent a significant leap forward in Redis security, enabling multi-tenant Redis deployments and greatly improving the overall security posture of your applications. Having explored how to connect, command, and control Redis, we're now ready to pivot our focus from fundamental interactions to the critical aspects of performance and scalability, which are key to deploying Redis successfully in production. Chapter 4, Understanding Redis Performance. Redis has earned its reputation as a blazing fast data store, but its speed isn't magic. It's the result of meticulous design, leveraging efficient data structures, and a carefully optimized architecture. To truly master Redis, it's essential to understand the forces that drive its performance, how to measure it, and what factors can hold it back. This chapter dissects the core components of Redis's performance model, equipping you with the knowledge to identify bottlenecks and lay the groundwork for effective optimization. 4.1 The Redis Performance Model. CPU, Memory, Network. Redis's performance is primarily governed by three fundamental resources: CPU, memory, and network, I/O. Understanding how Redis interacts with each of these is key to diagnosing and improving its throughput and latency. CPU utilization, the single-threaded event loop. As introduced in Chapter 1, Redis is predominantly single-threaded for command processing. This means that a single CPU core is responsible for executing all client commands and managing the in-memory data structures. This design simplifies consistency and atomicity, eliminating the need for complex locking mechanisms that plague multi-threaded databases. However, this single-threaded model also implies that Redis can only utilize one CPU core for its main workload. If your Redis instance exhibits 100% CPU utilization on that core, it's operating at its maximum command processing capacity. Any further increase in requests will lead to increased latency as commands queue up. While the main thread handles commands, some operations, like AOF rewrites and RDB saving discussed later in this chapter, are delegated to background threads or separate processes using operating system calls like fork. These background operations can cause temporary spikes in resource usage, but don't directly block the main command processing thread. Memory footprint and management. Redis is an in-memory data store. This is its secret to speed. Accessing data from RAM is orders of magnitude faster than accessing it from disk. Consequently, the amount of available RAM directly dictates how much data Redis can store. Memory management in Redis is sophisticated. It includes efficient encoding of data structures, e.g., using ziplist for small lists and hashes to save space. But it also means you must carefully size your instance. If Redis attempts to use more memory than available, the operating system might resort to swapping, moving data from RAM to disk, which dramatically degrades performance and can lead to instability. Key configurations like max memory, which sets a memory limit, and max memory policy, which determines what Redis does when the limit is reached, like evicting data, are crucial for managing memory effectively, and we will explore them further in this chapter. Network I/O, latency and bandwidth. Every Redis command involves network communication between the client and the server. This introduces network latency, the time it takes for a request to travel from client to server and back, and consumes network bandwidth. For Redis's sub-millisecond response times to be apparent, network latency must be minimal. A significant portion of the total time for a Redis operation may be spent just in network travel, not in the Redis server itself. High network latency, e.g., due to geographical distance, network congestion, or inefficient client-side practices, can drastically reduce the effective throughput, commands per second, your application observes, even if the Redis server itself is perfectly healthy. Similarly, insufficient network bandwidth can become a bottleneck if you are transferring very large amounts of data to or from Redis, such as big string values or the results of SMEMBRS on huge sets. 4.2 Benchmarking and profiling Redis. Understanding how Redis performs in your specific environment and with your workload is paramount. Raw numbers and theoretical limits are useful baselines, but real-world performance can vary. Redis provides excellent built-in tools for basic benchmarking and profiling. Using Redis Benchmark. The Redis Benchmark utility, included with the Redis distribution, is a simple yet powerful tool for stress testing your Redis instance. It simulates multiple clients sending commands concurrently and reports throughput, requests per second, and latency distribution. You can specify the command to benchmark, e.g., set, get, lpush, the number of requests to perform, the number of concurrent clients, the size of the values. An example command might look like Redis benchmark tset get n100,000 c50d 100. This runs 100,000 set and 100,000 get requests with 50 concurrent clients, using 100 byte values. The output provides average latency, P50, P90, P99, and P99.9 latency figures, and the total requests per second, giving you a comprehensive picture of performance under load. The info command, your performance dashboard. The info command, briefly mentioned in Chapter 3, is an invaluable source of real-time operational statistics for your Redis instance. It returns a detailed report, broken down into sections, that allows you to monitor key performance indicators. Info CPU shows CPU utilization by Redis, including system and user time and background processes. Info memory provides insights into memory usage, including used memory, the total amount of bytes allocated by Redis, used memorius, the resident set size, or memory actually held by the process in RAM, and details on memory fragmentation. Info clients shows the number of connected clients and their statistics, including input-output buffer sizes. Large buffers can indicate slow clients or network issues. Info stats contains cumulative statistics on commands processed, total comments processed, connections, keys expired and evicted. Info persistence details on RDB and AOF persistence, including last save times, status of background saves, and AOF buffer size. Info replication crucial for monitoring master replica setup, including replication lag. Regularly querying info or using monitoring tools that do so automatically allows you to identify trends, detect anomalies, and pinpoint potential bottlenecks related to CPU, memory, or I/O. Slow log, identifying slow commands. Despite Redis's speed, some commands can take longer to execute, especially if they operate on very large data structures or involve complex computations. The slow log feature is designed to identify and record these commands. Redis itself does not consider network or client-side latency in slow log. It only logs commands whose execution time on the server exceeds a configured threshold. Two key configuration parameters control slow log behavior in redis.conf. Slow log slower than. This sets the threshold in microseconds. Commands executing longer than this time are logged. A common starting point is 1000 microseconds, 1 millisecond. Slow log maxlen. This sets the maximum number of entries to keep in the slow log in memory. The slow log is capped to prevent it from consuming excessive memory. You can inspect the slow log using Redis CLI slow log get count. Each entry includes a unique ID, Unix timestamp, execution duration in microseconds, the command itself, and the client's IP address and port. Analyzing slow log frequently can reveal problematic commands, e.g., keys in production, SMEMBRS on very large sets, or complex Lua scripts that are blocking the server, guiding your optimization efforts. System-level monitoring. Beyond Redis's internal tools, standard operating system monitoring utilities are essential, TOP or HTOP, for overall CPU, memory, and process resource utilization. VMstat provides insights into virtual memory statistics, paging, swapping, and CPU activity. IOStat monitors disk I/O activity, useful for assessing the impact of persistence. Network monitoring tools, e.g. Netstat, SS, IFTOP, to check network activity, open connections, and bandwidth usage. These tools help you determine if a performance issue is specific to the Redis process or if it's a broader system-level problem. 4.3 persistence and its impact on performance. As an in-memory data store, Redis is incredibly fast. However, if the server crashes or restarts, all data would be lost without a persistence mechanism. Redis offers two primary ways to persist data to disk, each with different performance implications. RDB, Redis database, snapshots, and the AOF, append-only file. RDB, Redis database file. Point-in-time snapshots. RDB persistence works by periodically creating a compact, binary representation of the Redis dataset and saving it to disk. This is done by a background child process, which fork S from the main Redis process. The child process writes the RDB file while the parent continues to serve client requests. Advantages. RDB files are very compact, saving disk space and faster for transfers, and they are optimal for disaster recovery because they can be loaded quickly on startup. Disadvantages. Data loss potential. If Redis crashes between snapshots, any data changes made since the last successful snapshot will be lost. Performance impact. The fork operation involved in creating the RDB snapshot can be momentarily blocking for the main Redis thread, especially on systems with large amounts of memory or slower CPUs. During fork, the operating system needs to duplicate the process's memory mappings, which can take tens or hundreds of milliseconds for multi-gigabyte datasets. This leads to temporary latency spikes during a snapshot. I/O spikes. Writing the RDB file to disk also generates significant disk I/O, which can contend with other disk operations on the server. AOF, append-only file. Transaction log. The AOF persistence records every write operation received by the Redis server as a sequence of commands. This creates a log that can be replayed to reconstruct the dataset upon restart. Advantages. Higher durability. AOF can provide much better data durability than RDB, especially with the always fsync policy, though this has significant performance costs. Less data is lost in the event of a crash. Easier recovery. The AOF is a sequential log, making it less prone to corruption and easier to repair using Redis checkaof. Disadvantages. Larger file size. AOF files are typically much larger than RDB files for the same dataset because they contain a chronological sequence of commands rather than a compressed snapshot. Slower restarts without AOF rewrite. Replaying a large AOF file can take considerable time during Redis startup. To mitigate this, Redis supports AOF rewrites, which compact the AOF file by generating a new, smaller AOF that achieves the same dataset state. This rewrite process also uses a fork operation. Performance impact. The frequency of disk synchronization, fsync, directly impacts performance and durability. Always, fsync after every command. Highest durability, but extremely slow, e.g., 100x slower than no fsync, and usually not recommended for production. Eversec, fsync once per second. A good balance between durability and performance. Most popular choice. No, let the operating system decide when to fsync. Least durable, but fastest. The choice between RDB, AOF, or a combination of both depends heavily on your application's data durability requirements against acceptable performance trade-offs. 4.4 Memory management and optimizations. Efficient memory usage is critical for Redis performance and stability. Mismanaging memory can lead to out-of-memory errors, swapping, and severe performance degradation. Understanding used memory and used memorious. Used memory. This metric from info memory represents the actual memory consumed by Redis for its data and internal structures, as reported by Redis itself. Used memorious. The resident set size, reported by the operating system, is the amount of physical memory, RAM, consumed by the Redis process. Used memorious can often be larger than used memory due to memory fragmentation, overhead from the operating system's memory allocator, or memory shared by child processes during fork. Managing memory fragmentation. When Redis allocates and deallocates memory for keys and data structures, it can lead to memory fragmentation, where free memory is scattered in small, unusable chunks. This can cause used memorious to grow larger than used memory, meaning Redis is taking up more physical RAM than strictly necessary for its data. Redis 4.0 introduced active defragmentation, a background process that attempts to reclaim fragmented memory without blocking the server. This can be configured in redis.conf and usually provides a good balance between memory efficiency and performance. Eviction policies. When your Redis instance reaches its configured max memory limit, Redis needs a strategy to decide which keys to evict to make space for new data. This is controlled by the max memory policy setting. Choosing the right policy is crucial, especially when Redis is used as a cache. Noviction. Default, new writes are rejected when memory limit is reached, returns an error on write attempts. All keys LRU. Evicts keys least recently used LRU from all keys. This is generally a good choice for generic caching. Volatile LRU. Evicts LRU keys only among those that have an expiry set. Useful if you have a mix of persistent and volatile data. All keys LFU. Evicts keys least frequently used LFU from all keys. LFU is typically better than LRU at predicting what data will be needed in the future based on past usage patterns. Volatile LFU, evicts LFU keys only among those that have an expiry set. All keys random, evicts random keys from all keys, not very effective for caching. Volatile random, evicts random keys only among those that have an expiry set. Volatile TTL, evicts keys with the shortest time to live TTL from those with an expiry set. The choice of eviction policy depends on whether you have a mix of data, some with TTL, some without, and which data is truly least useful for your application. Max memory configuration. Setting a max memory limit in Redis.conf is essential in production. Without it, Redis will continue to consume memory until the server runs out, potentially causing the operating system to kill the Redis process or other processes on the machine. Max memory should be set to a value comfortably below your server's total available RAM, leaving room for the operating system, other processes, and Redis's own RSS overhead. Data structure encoding for memory efficiency. Redis attempts to optimize memory usage by using efficient internal encodings for small data structures. For example, small lists can be stored as a zip list, and small hashes as a zip list or hash table where keys and values are tightly packed. This saves significant memory compared to using traditional linked lists and hash tables. Once a data structure grows beyond certain thresholds, e.g., number of elements, size of elements, Redis will automatically convert it to a less memory-efficient but more performant underlying representation, e.g., a full hash table or linked list. This automatic optimization is typically handled by Redis and requires little manual intervention. But it's good to be aware that inserting very large elements or many small elements can trigger these conversions, potentially impacting performance as data structures are re-encoded. 4.5 Network considerations. Latency and throughput. Network performance plays a pivotal role in the overall perceived speed of your Redis application. Even if Redis itself is performing optimally, network issues can introduce significant delays. Measuring network latency. Network latency is the time it takes for a single request-response cycle to complete over the network, excluding the Redis server's processing time. You can measure this using standard ping tools to estimate round-trip time, RTT, between your application server and the Redis server. High RTTs, e.g., hundreds of milliseconds, significantly limit the number of commands per second your application can send. Impact of high network latency on TPS. Consider a simple operation like a GET command. The total time for this operation is roughly network RTT plus Redis processing time. If Redis processes it in 100 microseconds and network RTT is 10 milliseconds, the network accounts for 99% of the latency for that single operation. For throughput, if each command takes 10 ms due to network, you can only achieve about 100 operations per second, regardless of how fast Redis is internally. Techniques to reduce network round trips. Since network latency can be a major bottleneck, the primary strategy to improve performance is to reduce the number of separate trips over the network. Pipelining. This is one of the most effective ways to boost throughput. Instead of sending one command and waiting for its response before sending the next, your client library can send multiple commands to Redis in a single network packet without waiting for individual responses. Redis processes them sequentially and sends back all responses in one go. Pipelining transforms many small network trips into one larger trip, effectively masking network latency. We will cover pipelining in detail in Chapter 5. Batching operations. Commands like mget, multi-get, and mset, multiset, allow you to retrieve or set multiple string keys in a single command. Similar to pipelining, this reduces distinct network requests. Lua scripting. As seen in Chapter 3, Lua scripts execute atomically on the Redis server. This means you can encapsulate complex logic involving multiple Redis commands within a single script. Sending this script over the network requires only one round trip, even if the script performs dozens or hundreds of internal Redis operations. This can dramatically improve the effective throughput for complex workflows. Network bandwidth. While less common than latency, insufficient network bandwidth can become a limiting factor if your application frequently transfers large amounts of data to or from Redis. This might happen if you routinely store and retrieve very large string values, close to 512 MB, or if you use commands that return large collections, e.g., SMEMBRS on a set with millions of members, LRANGE on a very long list. Ensure your network infrastructure, NICs, switches, can handle the required data flow for your Redis instances. Understanding these performance factors and continuously monitoring them will allow you to build and maintain highly optimized Redis deployments. In the next chapter, we'll delve into specific strategies for optimizing your data models and command usage within Redis to wring out even more performance. Chapter 5. Optimizing data models and commands. Having understood the fundamental performance characteristics of Redis in Chapter 4, we now turn our attention to practical strategies for optimizing your interactions with Redis. This chapter focuses on how your choices in data modeling and command usage directly impact performance. By carefully designing your keys, selecting the most appropriate data structures, utilizing efficient command patterns, and minimizing network round trips, you can significantly enhance the throughput and reduce the latency of your Redis-backed applications. 5.1 Principles of Efficient Key Design. The way you design your keys in Redis has a surprising impact on both memory efficiency and operational clarity. Since every key is stored in memory, optimizing their design is a fundamental performance best practice. Key naming conventions, readability, and consistency. Adopt a consistent and readable naming convention. This improves debugging, maintainability, and collaboration within your team. Common patterns include using colons to denote namespaces or hierarchy, e.g., user, 100, profile, product, SKU A123, cache, page, home. This allows for semantic grouping and makes it easier to understand the purpose of a key at a glance. Avoid excessively long key names. While Redis can handle them, they consume more memory and slight processing overhead. Keep them descriptive but concise. Minimizing key length for memory efficiency. Every character in a key consumes memory. If you have billions of keys, even saving a few bytes per key can result in significant memory savings. While readability is important, balance it with conciseness for high-volume key patterns. For example, U1, P might be chosen over user. 1. Profile for very high-frequency keys in a memory-constrained environment as long as it's well documented. For identifiers, use compact representations where possible, e.g., UUIDs are longer than simple integers but offer unique advantages. Choose what's appropriate for your scale and needs. Using namespaces and patterns for organization. As mentioned, colons or other delimiters create logical namespaces. This is particularly useful when different application components or microservices share a Redis instance. For example, cart, user, 123 for shopping cart data and session, user, 123 for user session data. These patterns are useful with commands like scan, discuss later, or for configuring ACLS, access control lists, by key pattern, as covered in Chapter 3. 5.2 Choosing the right data structure for the job. In Chapter 2, we discuss the various Redis data structures and their basic use cases. Here, we revisit them through a performance lens, emphasizing how selecting the optimal structure can drastically improve efficiency. Strings, best for simple key-value pairs, counters, binary data blobs, e.g., serialized objects, small images. Performance insight. Extremely fast O1 operations for GET and set. INCR DECR are atomic and also O1. Considerations. Storing very large strings, e.g., many MBS, can lead to higher memory fragmentation and longer response times when transferring data over the network. If you only need parts of a large string, consider chunking it or using a more granular structure. Hashes, best for representing objects or records with multiple fields. Performance insight. For a single object, a hash is more memory efficient than storing each field as a separate string key. Commands like HGET and HSET are O1. HMGET and HMSET are very efficient for fetching setting multiple fields in a single call. Considerations. Operations like HGTALL or ON, where n is the number of fields in the hash. If a hash contains tens of thousands or hundreds of thousands of fields, HGTALL can become a slow command, consuming significant CPU and network bandwidth. For large hashes, retrieve specific fields or use HSCAN for iteration. Lists, best for queues, FIFO, LIFO, event logs, message brokers. Performance insight. LPUSH, RPUSH, LPOP, RPOP are O1, making them ideal for high-throughput queue operations. The blocking BLPOP, BRPOP are also highly efficient for consumer patterns. Considerations. LINDEX and LRANGE scale with the size of the list. While LRANGE is generally fast for small to moderately sized ranges, retrieving elements from the middle of very long lists can be slow. If random access or searching within the list is frequent, consider a different structure or approach. Sets, best for unique item collections, membership testing, tracking distinct entities, supporting set intersection union difference operations. Performance insight, SADD, SISMEMBER, SREM are all O1 on average, making membership checks lightning fast. Set operations, SINTER, SUNION, SDIFF are highly optimized. Considerations, SMEMBRS, retrieving all members, is ON. For very large sets, this can be slow. Use SSCAN for iterating through large sets. Sorted sets, best for leaderboards, ranking systems, elements with priorities, basic time series data. Performance insight. ZADD, ZSCORE, ZREM are logarithmic O log n, which is very fast even for large sets. Range queries ZRANG, ZREVRANG, ZRANG-BYSCORE are efficient, scaling with the size of the returned range, not the entire set. Considerations. Operations that iterate over significant portions of a very large sorted set could still be slow, but they are generally optimized internally. Streams, best for event sourcing, persistent and reliable messaging, complex message queues with consumer groups. Performance insight, XADD append, is typically O1. Reading operations, XREAD, XREADGROUP are optimized for sequential access of new data. Considerations. Streams are designed for append-only logs. Random access or deletion of old entries within the stream is not efficient, though trimming from the head is. The guiding principle is, choose the data structure that naturally fits your data model and the operations you need to perform. Don't try to force a square peg into a round hole. Redis's optimized native structures usually outperform custom application-level logic built on less suitable primitives. 5.3. Command complexity and performance implications. Every Redis command has an associated time complexity, typically expressed in big O notation, e.g., O1, O log n, On. Understanding these complexities is crucial for writing performant applications, especially when dealing with large datasets. Avoiding O, N operations on large datasets. Commands with O, N complexity mean their execution time grows linearly with the number of elements, N, they operate on. While an ON command might be perfectly fine for a list of 100 items, it can become a significant performance bottleneck for a list of 10 million items. Common culprits for blocking the server due to ON behavior on large collections include keys pattern, as warned in Chapter 3, iterates over all keys in the database. HGTALL key iterates over all fields in a hash. SMEMBRS key retrieves all members from a set. ZRANG key 0-1 retrieves all members from a sorted set by rank. LRANG key 0-1 retrieves all members from a list. The power of scan and HSCAN, SSCAN, ZSCAN, iterative processing. For operations that require iterating over large collections, Redis provides a family of scan commands. These commands are designed to be non-blocking and efficient, allowing you to iterate over a collection incrementally without causing performance degradation. Scan cursor match pattern, count, iterates over keys in the current database. HSCAN key cursor match pattern, count, iterates over fields in a hash. SSCAN key cursor match pattern, count, iterates over members in a set. ZSCAN key cursor match pattern, count, iterates over members in a sorted set. These commands work by taking a cursor, initially 0, and returning a new cursor and a limited number of elements or fields members with each call. You continue calling scan with the returned cursor until it returns 0, indicating the iteration is complete. Example, conceptual, to process all elements of a large set named elusers. Cursor equals 0, while cursor equals 0. Result equals SSCAN elusers cursor count 100, fetch 100 at a time. Cursor equals result 0, update cursor for next iteration. Process result 1, process the fetched members. Scan commands guarantee that all elements present in the collection at the start of the iteration will be returned eventually, without blocking the server. 5.4 Pipelining requests, boosting throughput. One of the most effective ways to counteract network latency and significantly boost Redis throughput is pipelining. What is pipelining and why it's effective? Normally, when a client sends a command to Redis, it waits for the server's response before sending the next command. This request-response cycle often introduces significant latency due to the network round-trip time, RTT. Pipelining allows a client to send multiple commands to Redis in a single batch without waiting for individual responses. Redis processes these commands sequentially and then sends back all the responses in a single reply. Benefit: pipelining essentially amortizes the network RTT over many commands. If a single RTT is 1 ms and you pipeline 100 commands, the total time might still be around 1 ms plus server processing for 100 commands, instead of 100 ms for individual requests. This drastically increases throughput. How to implement pipelining? Conceptual. Most Redis client libraries provide native support for pipelining. The exact syntax varies by language, but the concept is universal. You typically enter a pipeline mode with your client. You execute multiple Redis commands as usual. The client library buffers these commands locally. You then execute a send flush command that sends all buffered commands to Redis in one go. The client receives a list of responses corresponding to each command sent. Conceptual example, illustrative, not actual code. Start a pipeline. Pipeline equals Redis client start pipeline. Add commands to the pipeline. They are buffered, not sent yet. Pipeline set, user 1 name, Alice. Pipeline get, user 1 name. Pipeline.anchor, page views. Pipeline get, page views. Execute the pipeline. All commands sent in one network trip. Responses equals pipeline execute. Access responses in order. Response 1 equals responses 0, OK from set. Response 2, responses 1, Alice from get. Response 3 equals responses to new count from INCR. Response 4, responses 3, new count from get. When to use and when not to use pipelining. Use when you need to send many commands in quick succession and don't need the result of command n before sending command n+1. This is common for bulk data ingestion, pre-populating caches, or updating multiple related keys. Avoid when your application relies on the result of a previous command to formulate the next one, e.g., get a value, then INCR it by a calculated amount. In such cases, multi exec transactions or Lua scripts might be more appropriate. The latency of an individual command is paramount, as pipelining groups commands and returns results at the end of the batch. The total size of the batched commands, or their combined responses, is extremely large, potentially causing large network packets or memory issues. 5.5 Batching operations with MGET, MSET, etc. Similar to pipelining, but at the command level, Redis offers specific commands that allow you to operate on multiple keys in a single round trip. These multi commands are highly optimized and should be preferred over sending individual commands in a loop, or even over pipelining if a single command can achieve the goal. MGET key retrieves the values of all specified string keys. Benefit: instead of NGET commands to fetch n keys, it's one MGET command, drastically reducing network overhead. Example: MGET user 1 name user 2 name user 3 name. MSET key value sets multiple string key value pairs simultaneously. This operation is atomic. Benefit: atomic update of multiple keys, and one network trip for many set operations. Example, MSET user, 1 name Alice user, 1 email alice@example.com. Other multi-key commands, del key, deletes multiple keys. Exisds key, checks existence of multiple keys. RPUSA checks key value, pushing multiple values to a list if the list already exists. SADD key member, adding multiple members to a set. ZADD key score member, adding multiple members to a sorted set. Whenever your application needs to perform the same operation on multiple independent keys, always check if an M command or a command that takes multiple arguments can do the job in a single request. 5.6 Lua scripting for atomic and efficient operations. As briefly mentioned in Chapter 3, Redis's Lua scripting engine is a powerful tool for performance and consistency. It allows you to execute an arbitrarily complex script on the Redis server as a single, atomic operation, reducing network trips for complex logic. If you have a business logic slice that involves several Redis commands and potentially conditional logic, executing it client-side would require multiple network round trips. Each trip introduces latency. With a Lua script, all these operations are encapsulated in a single EVAL or EVALSHA call, meaning only one network round trip, regardless of the script's internal complexity, ensuring atomicity for multi-command operations. Beyond just reducing network trips, Lua scripts are guaranteed to execute atomically. Once a Lua script starts executing on the Redis server, no other client command or script will be processed until the current script completes. This is a powerful property for maintaining data consistency, even for complex operations that involve reading, checking conditions, and then writing back. Case study: implementing a rate limiter efficiently with Lua. A common pattern for using Lua scripts is for rate limiting, e.g., limiting an API endpoint to 100 requests per minute per user. Consider a simple sliding window rate limiter. For a given user per minute, how many requests have they made? Without Lua, inefficient and non-atomic. GET user 123, rec count. Check if count equals limit. If so, reject. INCR user 123, rec count. If count equals 1, then expire user 123, rec count 60. This involves multiple network calls and is vulnerable to race conditions if two requests arrive concurrently from the same user. With Lua efficient and atomic, you send a Lua script like this. Local key equals keys1. Local limit equals ta-number, argv1. Local window size seconds equals ta-number, argv2. Increment the counter for this key. Local current requests equals redis.call incr. If this is the first request in the window, set its expiry. If current requests equals 1, then redis.call expire key. Window size seconds. And check if the limit is exceeded. If current requests limit, then return rejected. Else, return 1 allowed. And your application then calls EVAL with the script, keys e.g. user 123, rec count, and argv e.g. 100 for limit, 60 for window size. This entire logic executes atomically on the Redis server. This example showcases how Lua can encapsulate multi-step operations into a single atomic, network-efficient unit. Remember the caveats from Chapter 3. Keep scripts concise to avoid blocking the server, and ensure they are well tested. 5.7 Mitigating the N+1 problem in Redis. The N+1 problem, common in database interactions, also applies to Redis and can severely impact performance. It occurs when retrieving a collection of items, and then for each item in that collection, making a separate, additional query to fetch related data. This leads to N+1 queries, 1 for the initial collection, N for each related item. Identifying the problem. Imagine you fetch a list of resentencers e.g. using LRANGE. Then, for each user in that list, you perform a HGTALL to get their detailed profile. If there are 100 users, that's 1 LRANGE plus 100 HGTALL operations, resulting in 101 network round trips. Solutions. The solution is to minimize the number of round trips, often by fetching all necessary data in fewer, larger operations. Pipelining. Group the N individual commands into a single pipeline. This doesn't reduce the number of commands, but it drastically reduces the network RTTs to just one. Example: after LRANG to get user IDs, pipeline all HGTALL user ID calls and execute them together. Batching, MGET, HMGT, etc. If applicable, use multi-key commands. This is particularly effective for retrieving string keys, MGET, or specific fields from multiple hashes, HMGET. Example: if user profiles were simple strings like user, id, name and user, id, email, MGT user, one name user to name user, one email user to email. Data denormalization / composite keys. Sometimes, you can denormalize your Redis data model to store commonly accessed related data together. Example: instead of separate keys for user, 1, profile, a hash, and user, 1, lastActive, a string, if lastActive is always needed with the profile, perhaps it becomes a field within the user 1, profile hash. Example: for a feed, store essential user profile snippets directly within each feed item's string representation or as fields in a hash. Lua scripting. For more complex fetching logic, a Lua script can retrieve the initial collection, iterate through it on the server side, and then fetch related data, returning a composite result. This ensures everything happens in one atomic round trip. 5.8 Considerations for large items and collections. While Redis offers excellent performance, it's not a silver bullet for storing arbitrarily large pieces of data or managing extremely large collections without careful consideration. Impact of very large strings, hashes, lists, memory pressure. Extremely large individual string values, megabytes in size, or hashes lists set sorted sets with millions of members can consume disproportionate amounts of RAM. This increases usage memorius, potentially leading to swapping and defragmentation issues. Network bandwidth. Transferring a 50 MB string from Redis to your client consumes significant network bandwidth and client-side memory. Client buffer issues. Redis client output buffers can grow very large if you request huge amounts of data, potentially leading to client disconnection or memory exhaustion. Single-threaded blocking. While Redis is fast, processing a command that returns or manipulates a huge object, e.g., SMEMBERS on a 100 million member set, can cause a measurable blocking event for other pending commands, leading to latency spikes. Strategies for handling large data. Chunking. Break down very large string values into smaller, manageable chunks. Store these chunks across multiple keys and reconstruct them client-side. This might be more complex, but makes network transfer more resilient and allows for partial retrieval. Deduplication. If different keys store identical or highly similar content, consider storing the content once and having multiple keys reference its hash or ID. Alternative storage for blobs. For truly massive binary objects, e.g., large images, video files, Redis is generally not the optimal storage solution. Consider using dedicated object storage, e.g., AWS S3, Google Cloud Storage, and storing only metadata or pointers to these objects in Redis. Iterative access with scan for collections. As discussed for large collections, hashes, sets, sorted sets, use HSCAN, SSCAN, ZSCAN instead of commands that return all elements at once. This avoids large blocking operations and memory spikes. Data aggregation summarization. Instead of storing raw, highly granular data in Redis, preprocess and aggregate it into summary forms suitable for Redis. For example, instead of storing every single click event, store aggregated hourly click counts in a hash. By meticulously applying these optimization techniques, you can ensure your Redis application achieves maximum performance, efficiency, and stability, truly leveraging Redis as the high-speed data layer it's designed to be. The next chapter will build on these principles by exploring how to scale Redis to handle even larger workloads and datasets. Chapter 6. Scaling Redis, Replication, Sharding, and Clustering. As your application grows and user demand increases, a single Redis instance, no matter how powerful, will eventually hit its limits. This chapter delves into the strategies and technologies Redis provides to scale your data layer, ensuring high availability, improved fault tolerance, and the capacity to handle ever-increasing workloads and larger datasets. We'll explore the fundamental concepts of vertical and horizontal scaling, and then dive deep into Redis's built-in solutions: replication, sentinel, and cluster. 6.1 The need for scalability and high availability. In a production environment, simply running a single Redis server is rarely enough. There are two primary reasons why scaling and high availability become critical. Scalability: as your application gains more users or processes more data, a single server might become a bottleneck for throughput, the number of commands Redis can process per second. Latency: the time it takes for Redis to respond to a command. Capacity: the amount of data Redis can store in memory. Scaling aims to address these limitations by distributing the load or expanding resources. High availability, HA. A single point of failure is unacceptable for critical applications. If your sole Redis server goes down, your application might become unresponsive. HA ensures that your Redis service remains operational even if hardware fails, network issues occur, or software crashes. There are two main approaches to scaling a data store: vertical scaling, scaling up, increasing the resources, CPU, RAM, faster network of a single server. This is often the first step in optimizing performance. However, there are limits to how much you can scale a single machine, and it still leaves you with a single point of failure. Horizontal scaling, scaling out, distributing the workload across multiple servers. This provides greater scalability and high availability, as the failure of one server doesn't bring down the entire system. Redis primarily focuses on horizontal scaling. 6.2 Redis replication. Data redundancy and read scaling. Redis replication is the simplest and most fundamental way to achieve data redundancy and improve read scalability. It involves setting up one or more replica, or slave, instances that are exact copies of a master Redis instance. How replication works: when a replica connects to a master, it sends a synchronization command. The master performs a background save, RDB snapshot, and transfers this snapshot to the replica. While the snapshot is transferring, the master buffers all new write commands. Once the snapshot is received, the replica loads it, and then the master sends its buffered commands, catching the replica up. After the initial synchronization, the master continuously streams all write operations to the connected replicas. Replicas process these commands, ensuring their datasets remain in sync with the master. This is an asynchronous process, meaning the master doesn't wait for replicas to acknowledge writes before proceeding. Benefits of replication. Read scalability. Read operations can be distributed among the replicas, offloading the master and significantly increasing the read throughput of your system. This is a common pattern for high read volume applications. Data redundancy provides a copy of your data on separate machines. If the master fails, your data is still available on the replicas. Failover preparation. While replication itself doesn't provide automatic failover, it's the foundation upon which Redis Sentinel and Redis Cluster are built, allowing a replica to be promoted to a new master. Background operations offloading. You can configure replicas to handle persistence operations, RDB AOF saving, freeing the master from this potentially blocking work. Commands: replicaof masterip masterport. This command, issued on a replica instance, tells it to start replicating data from the specified master. Info replication. Running info with the replication section provides details on the current replication state for both master and replica instances, including connected replicas, replication offsets, and replication lag. Considerations. Replication lag. Because replication is asynchronous, there might be a small delay lag between the master and its replicas. If the master crashes, any data written to the master but not yet propagated to replicas could be lost. Master-replica consistency. Your application needs to decide whether to read from the master, for strict consistency, or from replicas, for eventual consistency and higher read throughput. If an application reads from an eventually consistent replica immediately after writing to the master, it might temporarily see stale data. 6.3 Redis Sentinel. Automatic failover and high availability. While replication provides data redundancy, it doesn't automatically detect master failures or promote a replica to master. This is where Redis Sentinel comes in. Sentinel is a distributed system designed to provide high availability for Redis deployments, handling automatic failover processes. What Sentinel is and its role. A Sentinel system consists of multiple Sentinel processes, typically running on different servers. These Sentinels continuously monitor your Redis master and replica instances. Its primary responsibilities are monitoring. Constantly checks if your master and replica instances are alive and behaving as expected. Notification can notify system administrators or other software systems that a Redis instance is malfunctioning. Automatic failover. When a master is detected to be down, Sentinel initiates a failover process. It agrees on the master's failure, votes for the healthiest replica, promotes that replica to master, and reconfigures other replicas to follow the new master. Configuration provider. Clients can query Sentinels to discover the current master's address, allowing them to reconnect seamlessly after a failover. Setting up a Sentinel cluster. You need at least 3 Sentinel instances for robust automatic failover. This prevents a single Sentinel from making an incorrect failover decision, false positive, and ensures that a majority of Sentinels can agree on a master state. Failover process explained. Subjectively down SDOWN, a single Sentinel detects a master instance is unresponsive. Objectively down ODOWN, a sufficient number of Sentinels, a quorum, agree that the master is down. Leader election. The Sentinels elect a leader among themselves to orchestrate the failover. Replica selection. The elected Sentinel leader chooses the best replica to promote based on factors like replication offset, state, and recent connection. Promotion. The chosen replica is promoted to master. Reconfiguration. Other replicas are reconfigured to replicate from the new master. Old master handling. When the old master eventually recovers, it's reconfigured to become a replica of the new master. Quorum, majority, and robustness. The concept of a quorum is central to Sentinel's reliability. It refers to the minimum number of Sentinels that must agree that a master is down before a failover can be initiated. This prevents split-brain scenarios and ensures consistency in failure detection. For example, if you run 5 Sentinels, a quorum of 3 means at least 3 Sentinels must agree on the master state. Application client perspective with Sentinel. Application clients should not directly connect to Redis master or replica. Instead, they should connect to the Sentinel cluster. Client libraries supporting Sentinel, most do, can then query the Sentinels to find the current master's address and connect to it automatically. This makes your application resilient to master failures without manual intervention. 6.4 Redis cluster. Horizontal scaling for large datasets. While Sentinel provides high availability for a single master replica set, Redis cluster is designed for genuine horizontal scaling, allowing you to automatically shard your data across multiple Redis nodes. It provides both high availability and scalability for large datasets that cannot fit into a single Redis instance's memory. Concepts. Sharding data across multiple nodes, hash slots. Redis cluster shards its data using 16,384 hash slots. Each key stored in the cluster is mapped to one of these hash slots using a consistent hashing algorithm, CRC16 hash of the key modulo 16,384. Each master node in the cluster is responsible for a subset of these hash slots. When a client wants to store or retrieve a key, it first determines which hash slot the key belongs to and then connects directly to the master node responsible for that hash slot. Cluster architecture, master nodes, replica nodes, gossip protocol. A Redis cluster typically consists of at least 3 master nodes. Each master can have 1 or more replica nodes, similar to Sentinel setups. Master nodes store different subsets of the overall dataset. Replica nodes provide redundancy and failover for their respective master nodes. If a master fails, one of its replicas is promoted to take its place. Gossip protocol. Cluster nodes constantly exchange information about their state, the state of other nodes, assigned hash slots, and potential failures using a peer-to-peer gossip protocol. This decentralized approach ensures that all nodes have a consistent view of the cluster without a central coordinator. Resharding and rebalancing data. Redis cluster supports dynamic resharding. You can add new master nodes to expand cluster capacity or remove existing nodes. The cluster automatically moves hash slots and their associated data between nodes without downtime, allowing for flexible scaling. This rebalancing process is managed by the cluster. Client interaction with Redis cluster, smart clients. Unlike connecting to Redis instances individually or via Sentinel, client libraries for Redis cluster are cluster-aware or smart clients. They connect to any node in the cluster to get an initial mapping of hash slots to nodes. When the client needs to access a key, it calculates the hash slot and then connects directly to the specific node that owns that slot. If a node has moved a slot, or if a failover has occurred, the node returns a MOVED or ASK redirection, and the smart client automatically updates its routing table and retries the request on the correct node. This makes cluster interactions seamless for the application. Advantages of Redis cluster. Linear scalability. You can add more master nodes to scale your dataset size and operations linearly. High availability. Automatic failover is built in. If a master node fails, one of its replicas quickly takes over, similar to Sentinel, but integrated within the sharding context. Partition tolerance. The cluster can continue to operate even if some nodes are unreachable or disconnected. As long as a majority of master nodes remain operational, and each hash slot has an available master or replica. Limitations of Redis cluster. Multi-key operations across slots. Operations involving multiple keys, e.g., MSET, MULTI exec transactions, Lua scripts, are only allowed if all involved keys map to the same hash slot. This is enforced to maintain atomicity and avoid complex distributed transactions. Lua scripting caveats. Lua scripts also follow the multi-key operation rule. All keys accessed by a script must reside on the same node, i.e., in the same hash slot. No multiple databases. Redis cluster only supports database 0.6.5 manual sharding strategies, pre-cluster or custom needs. Before Redis cluster became mature and widely adopted, or for applications with very specific sharding requirements, developers sometimes implemented manual sharding at the application level. Client-side sharding logic. The application code is responsible for determining which Redis instance a key should reside on. This typically involves hashing the key, or part of it, like a user ID, and mapping the hash value to a specific Redis server from a pool of servers. Drawbacks: increased application complexity. The sharding logic has to be implemented and maintained within the application. Difficulty of rebalancing. Adding or removing Redis servers or redistributing data is a manual and often painful process, usually involving downtime or complex data migration scripts. No automatic failover. If a sharded instance goes down, the application must handle the failure and potentially redirect requests, which isn't easy to build. Given Redis cluster's capabilities, manual sharding is generally discouraged unless you have extremely unique requirements that Redis cluster cannot meet. 6.6 Proxy-based sharding solutions, e.g., twemproxy, Codis. Another approach to horizontal scaling that predates or complements Redis cluster is using a proxy layer. Tools like Twitter's twemproxy or Codis sit between the application clients and multiple independent Redis instances. How proxies abstract sharding logic. Clients connect to the proxy, not directly to the Redis instances. The proxy receives client commands, applies its own sharding logic to determine which backend Redis instance should handle the request, forwards the command, and then sends the response back to the client. This abstracts the sharding complexity away from the application, making the multiple Redis instances appear as one large instance to the client. Benefits and considerations. Simplified client. Applications use standard Redis client libraries without needing cluster awareness. Supports operations across keys via proxy logic. Some proxies can handle multi-key operations that cross different Redis instances, e.g., by fetching data from multiple instances and merging results, though this can be complex. Centralized control. Simplifies management of the Redis instances. Introduction of a new single point of failure. The proxy itself can become a bottleneck or a single point of failure unless highly available, e.g., running multiple proxies with a load balancer. Additional latency, every request now has an extra network hop through the proxy. Operational overhead, you need to deploy and manage a separate proxy layer. While these solutions have their place, Redis cluster is often the preferred choice for native, highly available sharding due to its integrated design and direct client-to-node communication. 6.7 Best practices for scaling Redis. Regardless of the scaling strategy you choose, applying these best practices will help you build a robust and performant Redis deployment. Choose the right scaling solution for your needs. If you primarily need high availability and read scalability for a single large dataset, Redis Sentinel with replication is a strong choice. If your dataset is too large for a single machine, or you need extreme write throughput distributed across multiple nodes, Redis cluster is the way to go. Avoid manual sharding unless absolutely necessary. Monitor cluster replication health diligently. Use the info command, Redis CLI stat for quick checks, and dedicated monitoring tools, like Prometheus/Grafana or Commercial Solutions, discussed in Chapter 11, to constantly observe key metrics such as replication lag, node CPU, memory, and network utilization, number of connected clients, commands per second, key evictions. Plan for failures, node loss, network partitions. Design your client applications to handle connection errors, timeouts, and redirections gracefully. Assume that nodes will fail and that network partitions will occur. Test your failover procedures regularly. Capacity planning and load testing. Before deploying to production, estimate your workload requirements in terms of memory, CPU, and network bandwidth. Perform rigorous load testing using tools like Redis Benchmark, or more sophisticated ones, to validate your chosen architecture and identify bottlenecks under anticipated peak load conditions. Adjust your instance sizes and cluster topology as needed. Consider persistence strategies. As discussed in Chapter 4, persistence, RDB, AOF, has performance implications. Choose the right strategy or combination for your masters and replicas to balance durability and performance. In a cluster, masters handle their own persistence for their hash slots. By combining an understanding of Redis's architecture with robust scaling strategies and continuous monitoring, you can build a Redis data layer capable of supporting even the most demanding applications. With this foundational knowledge of performance and scaling, we'll now shift our focus to the practical Redis design patterns that leverage these capabilities to solve common architectural challenges. Chapter 7. Caching patterns with Redis. Caching is one of the most fundamental and impactful techniques for improving the performance and scalability of modern applications. At its heart, caching involves storing frequently accessed or computationally expensive data in a faster, more accessible temporary storage layer. Redis, with its in-memory speed and diverse data structures, is an exceptionally powerful tool for implementing various caching strategies. This chapter will guide you through the most common caching patterns using Redis, explore different cache invalidation mechanisms, discuss how to select the optimal data eviction policy, and address challenges like cache stampede. By the end, you'll possess the knowledge to design robust and highly effective caching layers for your applications. 7.1 Introduction to Caching and its Importance. Imagine a busy librarian who has to fetch every requested book from a distant archive. It would be slow and inefficient. Now, imagine a librarian who keeps the most popular books on a shelf right next to the counter. This is caching in action. Why cache? Performance enhancement, the primary motivation. Redis operates in memory, providing millisecond to microsecond response times. By serving data from Redis instead of a slower primary database, like a relational or NoSQL disk-based database, you dramatically reduce overall application latency for read-heavy workloads. Database load reduction. Caching shields your primary database from incessant read requests. This reduces the strain on your database's CPU, I/O, and network, allowing it to handle more write operations or simply function more efficiently under load. Cost savings. By reducing database load, you might be able to use smaller, less expensive database instances or postpone costly database scaling efforts. Key metrics. Cache hit ratio. the percentage of requests that are successfully served from the cache. A high hit ratio, e.g., 90% or more, indicates an effective caching strategy. Cache miss ratio, the inverse of the hit ratio, representing requests that necessitate fetching data from the slower backend. Each miss is an opportunity for optimization. Key concept: time to live, TTL. Many cached items have a limited lifespan. TTL, time to live, is a property assigned to a cached item, indicating how long it should remain valid in the cache before being considered stale and automatically removed. Redis natively supports TTL through commands like expire and directly alongside set with the X or PX options. 7.2 Cache aside pattern. The cache aside, also known as lazy loading or lazy caching, pattern is the most common and generally simplest caching strategy to implement. In this pattern, the application code is entirely responsible for deciding when to read from or write to the cache. Description: read operation. When the application needs data, it first checks the cache. Cache hit. If the data is found in the cache, a cache hit, the application retrieves it directly from Redis and returns it. Cache miss. If the data is not in the cache, a cache miss, the application fetches the data from the underlying primary database. Once retrieved, it stores a copy of this data in Redis, using, for example, a set command with an expire time before returning the data to the client. This population step ensures subsequent requests for the same data are served from the cache. Write operation. When the application modifies data, it first writes the updated data to the primary database. After the database write is successful, the application then explicitly invalidates or updates the corresponding entry in the Redis cache. Invalidating, deleting the cache entry is often simpler, forcing the next read to fetch the fresh data from the database and repopulate the cache. Implementation, conceptual. For reads, use GAT key. If the result is nil, query the database, then set key value x seconds. For writes, update the database, then del key, or set key new value x seconds if updating directly. Advantages: simplicity. Relatively easy to understand and implement within application logic. Resilience. The cache can fail independently of the database. If Redis is unavailable, the application can still function by directly querying the database, though with degraded performance. Only caches needed data. Data is only loaded into the cache when it's requested, preventing the cache from being filled with rarely accessed information. Disadvantages: potential for stale data. If the database is updated directly without the application explicitly invalidating the cache entry can become stale. This requires careful cache invalidation logic. Initial latency. The very first request for a piece of data will always be a cache miss, incurring the full latency of a database lookup. 7.3 Write-through pattern. The write-through caching pattern attempts to maintain strong consistency between the cache and the primary database by writing data to both layers simultaneously. Description: write operation. When the application wants to write or update data, it writes directly to the cache. The cache then synchronously writes this data to the primary database. The write operation is only considered complete once the data has been successfully written to both the cache and the database. Read operation. Reads are handled in the same way as the cache aside pattern. Check cache first, then database on a miss. Since the cache is updated synchronously on writes, it should always contain the most up-to-date data. Implementation, conceptual. A component could be a caching library or your application's data access layer, handles the write to both Redis, e.g., set key value, and your database within a single atomic-like unit. Advantages: strong consistency. The cache always reflects the most recent data because writes are applied to both the cache and the database at the same time. This simplifies application logic related to data freshness. Reads benefit immediately. Freshly written data is immediately available in the cache for subsequent read requests. Disadvantages: slower writes. Writes are slower than a cache-aside approach because the application must wait for two write operations, to cache and to database, to complete. Cache as a single point of failure. If the cache layer becomes unavailable or slow, it can directly impact the ability to write data to the database, potentially bringing down the entire write path. requires high availability for the cache itself. Filling with unused data. Data is written to the cache even if it's never read, potentially consuming cache resources unnecessarily. 7.4 Write-back, write-behind pattern. The write-back or write-behind caching pattern prioritizes write speed. Data is written directly to the cache, with the update to the primary database happening asynchronously at a later time. Description, write operation. When the application modifies data, it writes the changes only to Redis. Redis confirms the write, and the application can proceed immediately. Asynchronous synchronization. A separate process, often a dedicated background worker or a Redis daemon process, is responsible for reading the delayed writes from Redis, perhaps from a queue or a dirty items list, and flushing them to the primary database. Read operation. Reads are typically served directly from the cache. Implementation, conceptual. Application performs set key value. A background process, e.g., listening to a Redis stream or monitoring a periodically updated key, reads unpersisted changes from Redis and writes them to the database. Advantages, very fast writes. Writes are extremely fast from the application's perspective, as there's no waiting for the slower database interaction. This is ideal for write-heavy, low-latency applications. Reduced database load. Writes are batched and sent to the database in fewer, larger operations, further reducing database load. Disadvantages. Risk of data loss. If the cache, Redis, fails before the asynchronous write to the database occurs, data that was only in Redis could be permanently lost. This risk makes write-back unsuitable for critical data unless robust data durability and recovery mechanisms, like Redis's AOF persistence combined with a robust write-back mechanism, are carefully designed. Data consistency challenges. Data in Redis might temporarily be newer than data in the primary database, leading to potential consistency issues if other systems directly query the database. Increased complexity. Implementing a robust write-back strategy, with retries, error handling, and ensuring data integrity, is significantly more complex than cache-aside or write-through. 7.5 Cache invalidation strategies. One of the hardest problems in computer science is often quipped to be cache invalidation. Ensuring that cached data remains fresh and accurate is crucial. Here are common strategies. Time-based expiration, TTL. Description, the simplest and most common method. Each cached item is assigned a time-to-live TTL or an absolute expiration timestamp. Redis automatically removes the key once this time elapses. Implementation, using setx key seconds value or set key value x seconds. Pros, easy to implement, Redis handles cleanup automatically. Cons, data can be stale for the duration of the TTL if the source changes. Choosing the right TTL is often a balancing act between freshness and cache hit ratio. Event-driven invalidation. Description. Data is explicitly invalidated, deleted from the cache when its corresponding source data, e.g., in the primary database changes. Implementation. Typically involves a database trigger, an application hook, or a separate service that, upon data modification, issues a del key command to Redis. Redis pub/sub can also be used to broadcast invalidation messages. Pros, ensures cache freshness, minimizes stale data. Cons, increases coupling between source data updates and cache management. Can be complex to implement correctly for all possible data modification paths. Read-through write-through with auto-invalidation. Description. In more sophisticated caching systems, sometimes external to purely Redis-based patterns, the cache acts as an intermediary. On a cache miss, it automatically fetches data from the underlying source, read-through. On a write, it consistently updates its own copy and the source, write-through, often invalidating relevant entries. Pros. Transparency for the application simplifies implementation on the client side. Cons. Higher architectural complexity requires a powerful caching layer that handles both persistence and invalidation logic. Stale while revalidate. Description. A client requests data from the cache. If the cached data is stale, e.g., its TTL has expired, The cache immediately serves the stale data to the client while simultaneously initiating a background process to fetch the fresh data from the primary source. Once the fresh data is retrieved, the cache updates itself. Implementation requires application logic to manage a secondary background refresh even after an item's primary TTL expires. Pros: provides perceived low latency to the user. They get data immediately, even if slightly stale, avoids cache stampede on expiry. Cons: requires careful handling of the background refresh process and potential consistency issues during the stale but revalidating period. 7.6 Eviction policies revisited for caching. As discussed in Chapter 4, Redis uses eviction policies to decide which keys to remove when the max memory limit is reached. For caching, selecting the right policy is critical to maximizing the cache hit ratio and ensuring that the most valuable data remains in memory. Noviction, not a caching policy. It prevents new writes when memory is full. Only suitable if Redis is not primarily used as a cache or you manually manage evictions. All keys LRU, least recently used, a widely adopted and generally excellent policy for generic caching. It evicts the keys that have not been accessed for the longest time, assuming that recently accessed data is more likely to be accessed again. All keys LFU, least frequently used, evicts keys that have been accessed the fewest times. LFU can be more effective than LRU in scenarios where some data is accessed frequently for a short period, and then rarely, while other data is accessed consistently over a long period. LFU identifies the truly cold data better. Volatile LRU/volatile LFU. These policies are similar to their all keys counterparts, but they only consider keys that have an expire set. This is useful when you have a mix of persistent data that should never be evicted and volatile data used for caching. Volatile TTL evicts the keys that are closest to expiring. Useful if your primary freshness indicator is the TTL value itself. The choice between LRU and LFU often depends on your specific workload patterns. LFU requires a bit more CPU overhead because Redis needs to track access frequencies. Most general-purpose caches will perform well with all keys LRU. 7.7 Handling cache stampede, dogpiling. Cache stampede, also known as dogpiling or the thundering herd problem, is a common issue that occurs when a popular cached item expires. Many concurrent requests for that item suddenly become cache misses, all simultaneously hitting the primary database to fetch and repopulate the cache. This flood of identical requests can overwhelm the backend database, leading to performance degradation or even system crashes. Identifying the problem. A sudden, sharp spike in database queries and database CPU I/O immediately after a popular cached item's TTL expires. Degraded application response times for that specific data. Solutions using Redis, distributed lock e.g., using set with NX and X. Strategy. When a cache miss occurs and an item needs to be recomputed, the first process to arrive attempts to acquire a distributed lock for that specific key e.g., set rebuild lock key, locked NXX10. Process. If the lock is acquired, that process recomputes the data, updates the cache, and then releases the lock del rebuild lock key. Subsequent concurrent requests for the same key, finding the lock held, either wait for the lock to be released and then read from the newly populated cache, or serve slightly stale data if available, e.g., from an expired cache entry, while the recomputation happens. This ensures only one process revalidates and populates the cache. Probabilistic expiry/jitter. Strategy. Instead of setting a fixed TTL for all instances of a popular item, add a small, random jitter to their expiration times. If an item usually expires in 60 minutes, randomly make it expire between 55 and 65 minutes. Benefit. Spreads out the cache invalidation events over a time window, preventing a sudden surge of requests to the backend. Mutex and recomputing once, a variation often combined with stale while revalidate. Strategy. Serve expired content immediately, stale while revalidate, but for the background revalidation, use a mutex, like a Redis distributed lock, to ensure only one background process recomputes and updates the cache. Other background processes would detect the mutex and simply wait for the update or exit. Benefit: combines the best of immediate response with controlled backend load. 7.8 Advanced caching scenarios. Global caches, multi-layer caching. Caching can be deployed in simple or complex architectures depending on the scale and performance requirements. Global caches, distributed caching. Description: using a central Redis instance or cluster to cache data that is common across multiple application instances, microservices, or even geographically dispersed data centers. Benefit: reduces redundant data fetching across your entire distributed system. All application instances benefit from a shared cache, improving overall cache hit ratios. Redis's replication and clustering capabilities make it an ideal choice for building highly available and scalable global caches. Multi-layer caching. Description: combining different caching layers, each with varying characteristics, speed, capacity, cost, to create a hierarchical caching strategy. Common layers. In-process memory cache, level 1L1. Extremely fast, resides within the application's memory, e.g., and in memory hash map. Smallest capacity, fastest access. Data is lost when the application restarts. Redis distributed cache, level 2L2. Centralized Redis instances. Slower than in process but much faster than a database. Larger capacity, shared across all application instances, and can be persistent. This is typically the primary caching layer. Primary database, level 3L3, the ultimate source of truth, persistent but slowest. Flow: application first checks L1. If miss, checks L2 Redis. If still miss, queries L3 database, then populates L2 and L1. Benefit: provides optimal performance by serving hot data from the fastest cache, L1, while still leveraging the benefits of a shared, larger, and potentially persistent cache, L2, Redis. By strategically implementing these caching patterns and understanding their trade-offs, you can transform a slow, database-bound application into a highly responsive and scalable system, leveraging Redis's unique speed and versatility. Next, we'll explore how Redis powers real-time analytics and messaging patterns. Chapter 8: Real-time analytics and messaging patterns. Redis's speed, atomic operations, and versatile data structures make it an ideal choice not just for caching, but also for building dynamic, real-time applications. This chapter explores how Redis can be leveraged to implement solutions for real-time analytics, from basic counters to complex leaderboards, and for various messaging paradigms, including chat systems and robust message queues. These patterns are essential for creating highly responsive and interactive user experiences. 8.1 Real-time counters and aggregators. One of the most straightforward and powerful real-time applications of Redis is managing counters and aggregators. Its native INCR increment and HINCRBY hash increment by commands are atomic, meaning multiple clients can increment a counter concurrently without risk of race conditions or data corruption, ensuring accuracy even at high velocities. Simple counters. Scenario: tracking metrics like page views, likes on a post, content shares, or the number of downloads for a file. Application: a simple Redis string key can serve as a counter. Each time an event occurs, e.g., a page view, a command like INCR webpage, home, views is issued. Redis atomically increments the number stored at that key. If the key doesn't exist, it's initialized to 0 before incrementing. Benefit: extremely fast, efficient, and accurate for high-volume counting applications. You can also use INCRBY to increment by a specific value or DECR/DECRBY for decrements. Complex aggregations with hashes. Scenario: you need to count events but categorize them simultaneously. For instance, counting page views per browser type or sales per product variant. Application: a Redis hash can be used where the hash key represents the main entity, e.g., web page, home, views, browser, and the fields within the hash represent the categories, e.g., Chrome, Firefox, Safari. Each time a view occurs, you use HINCRBY web page, home, views, browser Chrome, 1 to increment the count for that specific browser. Benefit: allows for compact storage and easy retrieval of segmented aggregate data. You can get total views by summing the hash fields or specific browser views with HGET. Time series aggregations. Scenario: tracking metrics over time, such as hourly unique visitors, daily active users, or weekly revenue. Application: you can create separate counters or hash aggregators for different time intervals, e.g., INCR web page, home views, 2024 to 3:15:10 a.m., HINCRBY sales, 2024 Q1 product A5. While manual management of these keys can be done, specialized solutions like the Redis time series module, discussed in Chapter 12, provide more advanced capabilities for time series data. 8.2 Leaderboards and Ranking Systems. Creating dynamic leaderboards and real-time ranking systems is a classic use case for Redis, perfectly suited by its sorted sets data structure. Sorted sets ensure that members are always ordered by their associated scores, making rank retrieval and updates incredibly efficient. Implementing with sorted sets. Scenario: a gaming application needs to display top players by score, or a news portal wants to rank articles by popularity. Application: a Redis sorted set key can represent the leaderboard, e.g., game, high scores. Each player's ID would be a member, and their score would be the associated numerical score. When a player completes a game or earns points, their score is updated using ZADD game, high scores player score, player, Alice. If Alice already exists, her score is updated, and her position in the leaderboard automatically adjusts. Retrieving ranks: to get the top N players. ZREVRNG game, high scores 0N1 WITHSCORES. To find a specific player's rank. ZRENK game, high scores, player Alice, ascending rank, or ZREVRNK, descending rank. To get players within a score range. ZRANGBYSCORE game, high scores, min score, max score. Benefit: constant time, O log n, updates and efficient retrieval of ranges and ranks, making them ideal for constantly changing leaderboards. Handling tie-breaking: when multiple members have the same score, Redis sorts them lexicographically by their member name. If you need a different tie-breaking mechanism, e.g., by timestamp of when the score was set, you'd typically incorporate the tie-breaking logic into the score itself, e.g., derive a composite score that includes a timestamp, being careful with floating point precision, or retrieve ties, and then sort them client-side. Pagination for leaderboards. ZRANGE and ZREVRNG support start and stop indices, making it easy to paginate through large leaderboards by fetching specific chunks, e.g., ZRANGE game, high scores 1019 WITHSCORES for the second page of 10 players. 8.3 Rate limiting. Rate limiting is crucial for protecting your APIs and services from abuse, preventing denial of service, DoS, attacks, and ensuring fair usage. Redis's atomic operations and TTL capabilities make it a perfect fit for implementing various rate-limiting algorithms. Fixed window counter pattern. Scenario: limiting a user or an IP address to a fixed number of requests within a specific time window, e.g., 100 requests per minute. Application: for each unique user IP address, user 123, maintain a Redis string key, e.g., rate limit, user 123, timestamp aufgerundet minute. When a request comes in, increment the counter using INCR rate limit, user 123 timestamp aufgerundet minute. If the counter is 1, meaning it's the first request in the window, set an expire on the key for the duration of the window, e.g., 60 seconds. Check if the incremented count exceeds the allowed limit. If so, reject the request. Benefit: simple to implement and very fast. Disadvantage: can allow a burst of requests at the very beginning and end of a window, potentially exceeding the true rate. For example, 100 requests at 0, 59 and 100 requests at 101 appear as 200 requests in 2 minutes, but consumed near instantaneously. Sliding window log with lists or sorted sets. Scenario: a more accurate rate-limiting approach that counts requests within a moving window, preventing bursts at window boundaries. Application: store a timestamp for each request made by a user in a Redis list or sorted set. On each request, add the current timestamp to a key, e.g., LPUSH rate limit, user 123 now timestamp. Trim entries older than the window duration, LTRIM or ZREMRNGBUSCORE. Get the current count, LLEN or ZCARD. If it exceeds the limit, reject. Benefit: more accurate rate limiting, avoids the fixed window burst problem. Disadvantage: more memory intensive and slightly slower than the simple counter for very high request volumes, as it stores individual timestamps. Using Lua scripts for atomic rate limiting logic. As highlighted in Chapter 5, wrapping the rate limiting logic within a Lua script, EVAL, is a best practice. This ensures the entire operation, check, increment, set expiry, is atomic and happens in a single network round trip, preventing race conditions that could allow users to bypass the limit temporarily and improving performance. 8.4 Building chat applications with PubSub. Redis's publish-subscribe, PubSub mechanism provides a simple, efficient foundation for real-time messaging, perfectly suited for features like chat rooms or live notifications where message delivery is fire and forget. One-to-many messaging. Scenario: a user sends a message to a chat room, and all other users currently in that chat room should receive it instantly. Application: each chat room corresponds to a Redis channel, e.g., chatroom, general, chatroom, support. When a user sends a message, the application acts as a publisher and uses the publish chatroom, general hello everyone command. All other connected clients, users in the chatroom, act as subscribers by issuing subscribe chatroom, general. As soon as a message is published to chatroom, general, Redis immediately pushes it to all actively subscribed clients. PSUBSCRIBE for pattern matching. You can also subscribe to patterns using PSUBSCRIBE channel, which is useful for listening to all chat rooms within a namespace, for instance. Limitations for persistence and message delivery guarantees. It's crucial to remember that Redis PubSub is inherently non-persistent. If a subscriber is offline or disconnected when a message is published, they will not receive that message when they reconnect. Redis does not store messages for later retrieval in its core PubSub implementation. There are also no built-in acknowledgements or delivery guarantees. For scenarios that require message persistence, guaranteed delivery, or complex consumer group patterns, Redis streams are the appropriate solution. 8.5 Implementing reliable message queues with lists, LPUSH BRPOP. While PubSub is for broadcasting, Redis lists are excellent for building reliable, simple point-to-point message queues, where messages need to be processed by only one worker. The blocking operations make this particularly efficient. Producer-consumer model. Scenario: deferring background tasks, e.g., image processing, email sending, from a web application to dedicated worker processes. Producer application. When a task needs to be performed, the web application acts as a producer and adds a task message, e.g., a JSON string with task details to the end of a Redis list. RPUSH task queue \action \resize image \ID \123 consumer worker. A separate worker application continuously waits for tasks. It uses a blocking pop command like blpop task queue 0, where 0 means block indefinitely until a message appears. When a message is pushed to task queue, one of the blocked workers will receive and remove it from the queue for processing. Benefit: simple to set up, highly performant, and ensures that each message is processed by only one worker. BLPOP prevents busy waiting, where a worker constantly polls an empty queue. Acknowledging message processing, simple approach. For a more robust queue, a worker might first move a message to a processing queue before fully handling it, and then remove it from the processing queue upon completion. If the worker crashes, messages in the processing queue can be requeued by a supervisory process. BRPOPLPUSH, source queue destination queue timeout, atomically pops a message from source queue and pushes it onto destination queue. This can be used to move a message from an incoming queue to a processing queue. A separate mechanism would then LREM it from the processing queue upon success. Limitations for complex scenarios. While list-based queues are powerful, they have limitations for message visibility. If a worker processes a message, there's no built-in tracking of its state. If the worker crashes, the message might be lost or stuck in the processing queue indefinitely without external logic. Requeuing on failure. Robust requeuing of failed messages requires manual implementation. No consumer groups, Unlike streams, there's no native concept of consumer groups in list-based queues, though you can implement a form of it to manage message distribution across many workers intelligently. 8.6 Event Streaming and Event Sourcing with Redis Streams. For the most robust and feature-rich messaging and event logging patterns, Redis Streams, introduced in Chapter 2, are the preferred choice. They offer persistence, ordered delivery, and sophisticated consumer group management, making them suitable for event sourcing, auditing, and building complex real-time data pipelines. Beyond simple queues, persistent, ordered multi-consumer groups. Scenario, capturing all changes as an immutable event log for auditing, replaying, or enabling multiple, independent services to react to the same events. Application. When an event occurs, e.g., a user-registered event, it's appended to a Redis stream using XADD user events key 1 value 1 key 2 value 2. Each event receives a unique, time-based ID. Consumer groups for scalable processing. Multiple worker services can form a consumer group to process the same stream. Each service identifies itself, e.g., XREADGROUP group mygroup myconsumer. Redis ensures that within that group, each message is delivered to only one consumer. This allows you to scale out your processing by adding more consumers to the group. Multiple consumer groups. Different applications can read from the same stream, each with their own consumer group, and maintain their own processing progress. For instance, one group processes user-registered events for analytics, and another for sending welcome emails without interfering with each other. Implementing event logs. Streams are ideal for logging every significant action or state change in your system. This immutable event log can be retained indefinitely or trimmed using XDRIM and replayed for debugging, data recovery, or building new derived views of data. Building microservice communication with streams. Streams serve as a powerful messaging backbone for microservices. Services publish events to dedicated streams, and other services subscribe to these streams using consumer groups to react to events relevant to them. This provides loose coupling and asynchronous communication. Error handling and message reprocessing. Redis streams provide sophisticated mechanisms for acknowledging successfully processed messages, XACK. Unacknowledged messages, XBNDING, can be inspected and claimed by other consumers in the group. Using XCLAIM, if a worker fails, ensuring messages are not lost and are eventually processed at least once delivery. Streams provide a robust and scalable foundation for event-driven architectures, offering significant advantages over simpler list-based queues for scenarios requiring high reliability and complex consumption patterns. 8.7 Real-time user activity tracking. Tracking user activity in real time is crucial for analytics, personalization, and operational insights. Redis, particularly through HyperLogLog and its native list stream hash data types, offers efficient solutions. Using HyperLogLog for unique visitor counts on a large scale. Scenario: needing to estimate the number of unique users who visited a page, an entire website, or performed a specific action, without storing every single user ID, which can be memory prohibitive for millions or billions of unique users. Application: for each user interacting with a resource, their unique ID is added to a HyperLogLog key, e.g., PFADD page, home, uniquevisitors, user, ABC. The PFCOUNT page, home, uniquevisitors command then gives a highly accurate estimate of the unique visitors, using a constant, incredibly small amount of memory, around 12 KB, regardless of the number of unique visitors. Benefit: enables counting uniques at a scale impossible with traditional methods, accepting a negligible margin of error. Recording recent activity with lists or streams. Scenario: displaying a user's recent actions, like recently viewed items, or showing a real-time feed of events happening across your platform. Application: lists. You can LPUSH items into a list, e.g., user 123, recently viewed product, XYZ, and use LTRIM to keep the list from growing too large, e.g., maintain only the last 10 viewed items. LRANGE then provides the feed. Streams. For a more robust and replayable activity log, use XADD user 123, Activitalog action viewed producted XYZ. This allows for richer data in each event and persistent storage. By combining these real-time analytics and messaging patterns, Redis empowers developers to build highly interactive, responsive, and data-driven applications that excel in today's fast-paced digital environment. The next chapter will expand on these patterns, focusing on how Redis can be used to solve challenges in distributed systems. Chapter 9: Distributed Systems Patterns. Modern applications are increasingly built as distributed systems, composed of multiple independent services that communicate with each other. While offering significant benefits in terms of scalability, resilience, and modularity, distributed systems introduce a new set of challenges. Ensuring consistency across services, coordinating actions, and managing shared state. Redis, with its high performance, rich data structures, and atomic operations, is exceptionally well-suited to address many of these distributed systems challenges, offering elegant and efficient solutions. This chapter explores several crucial distributed systems patterns where Redis shines, from ensuring mutual exclusion to managing shared state and coordinating distributed tasks. 9.1 Distributed Locks. Ensuring mutual exclusion. In a distributed system, multiple processes or threads might try to access and modify the same shared resource simultaneously. Without proper coordination, this can lead to race conditions, data corruption, or inconsistent states. A distributed lock is a mechanism that allows only one process at a time to acquire a lock and access a critical section or shared resource, thereby ensuring mutual exclusion across a distributed environment. The challenge of distributed locking. Unlike locks within a single process, e.g., mutexes, distributed locks are inherently more complex. They must contend with network partitioning, process crashes, and clock synchronization issues, making robust implementation difficult. Implementing a robust distributed lock with set with NX and PXX. Redis itself doesn't provide a built-in lock command, but its atomic set command, especially when combined with options introduced in Redis 2.6.12, can be used to implement a surprisingly robust distributed lock. The key command is set key value x seconds, px milliseconds, nx Roman 20. Key, the name of the lock, e.g., resource 123 lock. Value, a unique identifier for the lock holder, e.g., a UUID or client ID. This is crucial for safely releasing the lock. NX, only set the key if it does not exist, acquire the lock. X seconds or px milliseconds, set an expiry time for the key. This is vital to prevent deadlocks if the client crashes while holding the lock. The lock will automatically be released after this time. Lock acquisition. A client attempts to acquire the lock. Set resource 123 lock miclientitude x10nx. If the command returns OK, the client successfully acquired the lock. If it returns nil, the lock is already held by another client. Lock release, safe release. A client holding the lock should only release it if it's the actual owner to prevent a different client from releasing a lock they don't own, e.g., if the original lock expired and another client acquired it. This requires a Lua script for atomicity. If redis.call get keys1 equals argv1, then return redis.call del keys1, else return 0. And this script checks if the value of the lock key matches the client's unique ID, and only then deletes the key. This prevents client A from releasing a lock that client B acquired after client A's original lock expired. Redlock algorithm and its controversies alternatives. For scenarios requiring an even higher degree of safety and partition tolerance, e.g., ensuring a lock is held even if a majority of Redis nodes fail. Salvatore Sanfilippo, anti-res, proposed the redlock algorithm. Redlock involves attempting to acquire the lock on multiple independent Redis instances, e.g., 5 distinct masters from different logical physical machines. A client acquires the lock if it can get it from a majority of these instances within a very short timeframe. Pros: designed for higher safety guarantees in highly unreliable distributed environments. Cons: redlock is significantly more complex to implement and manage. It has also been the subject of debate among distributed systems experts regarding its theoretical guarantees and practical applicability, especially concerning clock synchronization issues. Many applications might find a single-instance Redis distributed lock with careful expiry and safe release sufficient, often preferring to focus on idempotency and retry mechanisms in their application logic rather than relying solely on complex distributed locking. 9.2 Session Management and State Storage. For stateless web applications and microservices, Redis is an excellent choice for storing user sessions and other volatile application state. It provides a shared, centralized, and fast storage layer that allows any application instance to retrieve a user's session data. Storing user session data in Redis. Application. When a user logs in, a unique session ID is generated and stored in a cookie on the client's browser. The actual session data, e.g., user ID, permissions, shopping cart contents, last activity timestamp, is stored in Redis, typically using a hash data structure, session, sessionid, field value. HSET session UBXIS, userid, 123 roles, admin editor, last access, timestamp. Expiry. Sessions nearly always have a time to live TTL to manage memory and enhance security. Expire session UBXIS 3600 for 1 hour. Retrieval. On subsequent requests, the application retrieves the session ID from the cookie, then fetches the session data from Redis using HGTALL session UBXIS. Benefit. Enables horizontal scaling of web servers since any server can handle any request after fetching the session from Redis. Reduces load on the primary user database for frequent session lookups. Scaling web applications with shared session state. By externalizing session state from individual application servers to Redis, you remove the sticky session requirement, where a user's requests must always go to the same application server. This allows load balancers to distribute traffic more evenly, leading to better utilization of application server resources and increased fault tolerance. 9.3 Building a distributed task queue with Redis, advanced. Building upon the basic list-based message queues discussed in Chapter 8, Redis can form the backbone of more advanced, distributed task queue systems, especially when leveraging Redis streams. Comparison of list-based queues versus stream-based queues. Lists, LPUSH BLPOP. Simple, fast, guarantees single consumer processing within a blocking call. Good for basic, immediate task dispatch. Limitations include no persistence confirmation for messages, manual handling of worker crashes, and no built-in consumer group semantics. Streams, XADD, XRADGROUP, offer a persistent, ordered log with message IDs, message acknowledgement, XACK, pending message tracking, XBNDING, and robust consumer groups. Persistence. Messages written to a stream persist until explicitly trimmed. Consumer groups. Multiple, independent groups of consumers can read from the same stream, and within a group, Redis manages message delivery to individual consumers at least once delivery. If a consumer fails, messages are still tracked as pending and can be claimed by another consumer in the group. Replayability. The log nature allows messages to be replayed, crucial for debugging or disaster recovery. Implementing task retry mechanisms with streams. When a consumer reads a message from a stream within a consumer group, the message is marked as pending. If a consumer fails to process a message and doesn't XACK it within a certain time, checked via XBNDING idle, another consumer in the group can XCLAIM ownership of that message, effectively retrying the task. This provides inherent fault tolerance. Handling dead letter queues, DLQ. If a message consistently fails after multiple retries, it can be moved to a dead letter queue, another Redis stream or list, for manual inspection, ensuring failed messages don't block the main processing queue indefinitely. Workers pulling tasks, atomically marking as processing. The XREADGROUP command inherently supports this. A consumer group member performs an atomic read, and Redis manages the visibility of that message to other consumers within the group. 9.4 Idempotent operations with Redis. An idempotent operation is one that, when applied multiple times, produces the same result as if it had been applied only once. In distributed systems, where network errors can lead to retries, designing idempotent operations is crucial to prevent unintended side effects, e.g., double charging a customer or sending duplicate notifications. Redis can help implement idempotency checks, ensuring an operation executes only once. Strategy: for each operation that must be idempotent, generate a unique operation ID, e.g., a UUID or a hash of the operation's parameters. Before executing the core logic of the operation, check if this operation ID has already been processed. Application: client generates operation ID. Server receives request with operation ID. Server attempts to setnx processed operation ID 1, set only if not exist. If setnx returns 1, meaning the key was set, thus first time seeing this ID, proceed with sensitive operation, e.g., process payment. If setnx returns, meaning the key already existed, thus duplicate ID, return a success message immediately without reprocessing. Expiry: add a TTL to the processed operation ID key, e.g., set processed 1x86400NX to clean up old IDs. The TTL should be longer than any possible retry window. Benefit: provides a lightweight, fast, and atomic mechanism to ensure that retried requests do not cause duplicate side effects. 9.5 Feature Flag Management. Feature flags, also known as feature toggles, allow you to enable or disable features in your application remotely without requiring a code deploy. Redis is an excellent choice for storing feature flag configurations due to its speed and central accessibility. Using sets or hashes to store feature flags, global flags. For features that are simply on or off for everyone, a single string key can suffice. Set feature NUUI, true. User group specific flags. For A/B testing or rolling out features to specific user segments, Redis hashes or sets are perfect. Hash HSET feature NUUI users, userid1, true, userid2, false. Set SADD feature beta testers, userid1, userid2, check with SISMEMBR. Percentage rollout can be implemented with a combination of INCR for a sequential counter and checking against a threshold for user IDs. Dynamically disabling features. Your application reads the feature flag status from Redis at runtime. When you want to disable a feature, you simply update the corresponding Redis key. Changes are reflected almost instantly across all application instances. Caching flags. For performance, application instances can cache feature flags locally for a short period, e.g., 5 seconds. Use pubsub to send an invalidation message, publish, feature flag, update. Whenever a flag is changed in Redis, prompting applications to refresh their local caches. 9.6 Distributed Caching Revisited, Consistency and Coordination. While Chapter 7 covered caching patterns, using Redis as a distributed cache introduces challenges related to consistency and coordination across multiple application instances. Ensuring cache consistency across multiple application instances. Problem: if one application instance updates data in the primary database, how do other application instances, which might have stale versions of that data in their local or distributed Redis cache, become consistent? Read through, write through, as discussed. These aim for stronger consistency but have their own trade-offs. Event-driven invalidation, a common robust approach. When data changes in the primary database, the service responsible for the change publishes an invalidation event to a Redis pub subchannel. All other application instances subscribe to this channel, receive the event, and explicitly del the corresponding stale entry from their local caches, forcing a fresh lookup on the next request. Utilizing pubsub for cache invalidation propagation. Publisher, database update service, publish caching validation channel, user 123, profile. Subscribers, all application instances. Subscribe caching validation channel and then del user 123, profile upon receiving the message. Benefit: provides a highly efficient, lightweight way to propagate cache invalidation across distributed instances in near real time. 9.7 Designing Resilient Systems with Redis. Redis can also support the implementation of various resilience patterns to make distributed systems more robust. Circuit breakers and bulkhead patterns. You can use Redis as a central store for circuit breaker state. If a downstream service starts failing, your application can use Redis to update a shared counter or flag that indicates the circuit breaker is open. Subsequent calls to that service can then fail fast by checking Redis rather than attempting to call the failing service. The bulkhead pattern aims to isolate failures. For instance, you could store per-service rate limits in Redis, ensuring one service's high traffic doesn't drain resources meant for others. Degradation strategies when Redis is unavailable. While Redis is highly available, network issues or extreme load can sometimes make it temporarily unavailable. Your application should be designed to degrade gracefully rather than fail entirely. Fallback to database. If Redis used as a cache is unavailable, your application should fall back to querying the primary database directly, perhaps showing a warning or accepting slightly slower responses. Failover logic. For distributed locks, if Redis isn't reachable, your application might resort to a simplified, less robust local locking mechanism or halt operations on the critical resource entirely until Redis recovers. Graceful shutdown. Implement robust Redis client connection management with proper timeouts and retry logic to avoid cascading failures. By leveraging Redis for these distributed systems patterns, developers can build scalable, high-performance, and resilient applications that meet the demands of modern cloud environments. The next chapter shifts focus to a critical aspect of operational excellence, securing your Redis deployment. Chapter 10, Securing your Redis deployment. In the pursuit of performance and scalability, it's easy to overlook security, but doing so can have catastrophic consequences. A Redis instance, if left unsecured, can be a major vulnerability in your application's infrastructure, exposing sensitive data or providing an entry point for malicious activity. Redis's historical default of being accessible without authentication made it notoriously prone to misconfigurations if not properly secured from the outset. This chapter delves into the critical aspects of securing your Redis deployment, covering network configuration, authentication, data encryption, operating system best practices, and the safe management of powerful commands. Implementing these measures is not optional. It's a fundamental requirement for any production-ready Redis instance. 10.1 The importance of Redis security. Redis is an incredibly fast, in-memory data store. Its speed makes it a target. If an unauthorized entity gains access to your Redis instance, they could exfiltrate sensitive data. Session tokens, user profiles, cached personal information, financial data, or application secrets could be stolen. Manipulate data, alter data, leading to application malfunction, financial fraud, or data corruption. Launch attacks. Use your Redis instance as a launchpad for further attacks, e.g., executing arbitrary code, injecting malicious data, or launching denial-of-service attacks against other systems. Resource hijacking. Your Redis server could be used for cryptocurrency mining or other unauthorized activities, consuming your server resources and incurring costs. Common attack vectors against Redis often exploit open ports. Redis servers expose directly to the internet without proper firewalls. Weak or no authentication. Default configurations without require-pass or ACLS enabled. Vulnerable commands. Misusing powerful commands like flushall or debug. 10.2 Network security best practices. The first line of defense for any data store, including Redis, is robust network security. Simply put, if an attacker cannot reach your Redis server, they cannot compromise it. Binding to specific IP addresses, bind directive. By default, Redis might listen on all available network interfaces, bind 0.0.0.0. This is extremely dangerous in a production environment. Always configure Redis to bind only to specific IP addresses that your application servers can access. Example: if your application servers are on a private network, 10.0.0.0/16, bind Redis only to its private IP address or the loopback interface, 127.0.0.1, if both client and server are on the same machine. Configuration example in redis.conf. Bind 127.0.0.110.0.0.5. Firewall rules. Complementing the bind directive, use operating system-level firewalls, e.g., IPtables on Linux, Windows Firewall, or cloud provider security groups to restrict inbound traffic to the Redis port, default 6379, to only trusted IP addresses or subnets where your application servers reside. Block all other incoming connections to this port. Running Redis in a private network, VPC VNet. For cloud deployments, never expose your Redis instance directly to the public internet. Always deploy Redis within a virtual private cloud, VPC, virtual network VNet, or similar isolated network segment. Your application servers should be in the same private network or a peered one, and communicate with Redis using private IP addresses. SSH tunneling/VPN. For administrative access or for development environments, instead of opening the Redis port widely, establish a secure SSH tunnel or virtual private network (VPN) connection. This encrypts data in transit and restricts access to authenticated users of the VPN or SSH. TLS/SSL encryption, data in transit. While network isolation is strong, for environments where data traverses untrusted networks, e.g., highly regulated industries, hybrid cloud setups, transport layer security, TLS/SSL, encryption for data in transit is essential. Redis 6.0 Plus built-in TLS. Modern versions of Redis 6.0 and above offer native TLS support. This allows Redis clients and servers to authenticate each other and encrypt all communication. You enable TLS by configuring TLS port, TLS cert file, TLS key file, and TLS cert file in redis.conf. External proxies, e.g., Stunnel HA proxy. For older Redis versions or more complex setups, you can use an external proxy, like Stunnel or HA proxy, that handles TLS encryption-decryption, acting as a secure tunnel between your application and the Redis server. 10.3 Authentication. The RequirePass directive and ACLs. Once network access is controlled, authenticating legitimate clients is the next critical step. Historical RequirePass. Before Redis 6.0, RequirePass was the sole authentication mechanism. You'd set a password in redis.conf, e.g., RequirePass your strong password. All clients connecting to Redis would then need to send the auth password command before executing any other commands. Limitation. It's a single password for everyone, providing no granular control over what different clients can do. This makes it difficult to revoke access for specific services or to implement the principle of least privilege. Redis ACLS, access control lists. Granular authentication and authorization. Introduced in Redis 6.0, ACLS are a game changer for Redis security, providing a robust solution for authentication and authorization. As initially discussed in Chapter 3, ACLs allow you to define multiple users, create separate user accounts, assign granular permissions, control which commands each user can execute, e.g., allow GET but deny FLUSHALL, and which key patterns they can access, e.g., user 123. Vs config. Publish subscribe channel control. Limit which pub sub channels a user can subscribe to or publish on. No password option. You can even define users who require no password for unauthenticated access if needed for specific internal services on a highly secure network, though generally not recommended. Setting up an ACL user, example in redis.conf or via ACL setuser command. Create an admin user with a strong password that can do anything. User default off all keys at all plus at admin plus, at read plus, at write supersecret admin password. Create a cacheap user that can only read write to keys starting with cache. User cacheap on appcachepisword ~cache. Plus at read plus at write it all. Remember to use ACL save if you are modifying ACLs dynamically via Redis CLI. Or place them directly in the ACL file configured in redis.conf. Best practices for passwords tokens. Strong passwords. Always use long, complex, and unique passwords for Redis users. Avoid common words or patterns. Password management. Do not hardcode passwords in your application code. Use environment variables, secure configuration management systems, or secrets management services, e.g., AWS Secrets Manager, HashiCorp Vault. Rotate credentials. Periodically rotate your Redis user passwords. 10.4 Data Security Principles. Beyond network and access control, considering the security of the data itself is crucial. Encryption at rest. Redis, by design, stores data in plain text in memory. When it persists data to disk, RDB snapshots, or AOF files, these files also contain data in plain text. Operating system level. To protect data at rest, encrypt the underlying storage where Redis persistence files are stored. This can be done using full disk encryption, FDE, or encrypted file systems provided by your operating system or cloud provider, e.g., Amazon EBS encryption, Azure disk encryption. Transparent to Redis. Redis itself does not perform disk encryption. It relies on the underlying infrastructure. Data masking/tokenization. For highly sensitive data, e.g., credit card numbers, social security numbers, consider client-side encryption, masking, or tokenization before storing it in Redis. This means Redis never holds the actual sensitive plaintext. Even if the Redis instance were compromised, the stolen data would be encrypted or tokenized and rendered useless without the corresponding decryption keys or tokenization service. Auditing and logging access. Configure Redis to log connections, authentication attempts, and errors. Integrate these logs with your centralized logging system and security information and event management (SIEM) tools. Regularly review logs for suspicious activity, failed login attempts, or unauthorized command usage. 10.5 Operating System Security. The security of your Redis instance also depends on the underlying operating system it runs on. Running Redis with a non-root user. Never run the Redis process as the root user. Create a dedicated, unprivileged user, e.g., Redis with minimal permissions. This limits the damage an attacker can do even if they manage to compromise the Redis process. Ensure the Redis user only has read-write access to necessary directories, e.g., data directory, log file directory. Limiting open file descriptors. Redis can handle many client connections and files for persistence. Ensure the operating system's limit for open file descriptors, ulimit n, is set high enough to prevent Redis from running out of file handles, but not excessively high. Typically, 10,000 or more is suitable for production. Disabling transparent huge pages, THP. While not strictly a security measure, THP, transparent huge pages, on Linux can cause significant performance and latency issues for Redis, sometimes leading to unexpected memory usage and server instability. Disable THP for optimal Redis performance and stability. 10.6 Removing dangerous/unnecessary commands. Redis has several commands that, while useful for debugging or specific scenarios, can be extremely dangerous if exposed to untrusted clients in a production environment. Commands to consider disabling or renaming in production. Keys. As discussed, this command is ON and can block the server for very long periods on large datasets. Attackers could use it for reconnaissance or a simple DOS. FLUSHALL, FLUSHDB. These commands wipe out all data in the Redis instance or a specific database. An attacker could easily sabotage your application. Debug allows for risky operations like crashing the server intentionally. Shutdown shuts down the Redis server. CONFIG can be used to inspect or modify Redis configuration remotely, which is a significant security risk. SLAVEOF or REPLICOF in Redis 5+ can turn a master into a replica, potentially causing data loss. Monitor allows inspection of all commands processed by the server, potentially exposing sensitive data. Using rename command in redis.conf, you can disable a command by renaming it to an empty string, or rename it to something obscure if you need it for administrative purposes, but want to prevent common attacks that target the original command name. Example in redis.conf, rename command FLUSHALL, rename command FLUSHDB, rename command keys, rename command CONFIG, rename command debug, rename command shutdown, SHUTDOWNADMIN only. This completely removes FLUSHALL, FLUSHDB, keys, CONFIG, debug, and renames shutdown. 10.7 Security in a clustered environment. Securing a Redis cluster presents additional considerations beyond single instances. Securing internode communication. In a Redis cluster, nodes communicate with each other using a gossip protocol and exchange data. This internode communication should ideally be secured, especially if nodes are deployed across different networks or not in a perfectly isolated private network. Redis 6.0 plus TLS support extends to cluster bus communication. ACLS in cluster. ACLs apply uniformly across a Redis cluster. Permissions regarding keys will be enforced by the specific node handling the key based on its hash slot. Challenges unique to clusters. Ensuring all nodes in a cluster have consistent security configurations, e.g., all have ACLS enabled, all use TLS, can be an operational challenge. Use configuration management tools to ensure uniformity. Implementing a comprehensive security strategy for Redis requires a multi-layered approach, combining network isolation, robust authentication and authorization, data protection, and secure operational practices. By prioritizing these measures, you can confidently deploy Redis as a secure and vital component of your application infrastructure. Our next chapter will delve into another crucial operational aspect: monitoring, troubleshooting, and maintaining your Redis deployments. Chapter 11: Monitoring, Troubleshooting, and Maintenance. Deploying Redis in production is only the first step. To ensure sustained performance, high availability, and data integrity, continuous monitoring, vigilant troubleshooting, and proactive maintenance are absolutely essential. This chapter provides a comprehensive guide to mastering the operational aspects of your Redis deployments, equipping you with the tools and knowledge to keep your instances healthy and responsive. 11.1 The Pillars of Monitoring. Effective monitoring is the bedrock of operational excellence. It allows you to detect issues early, identify problems before they impact users, diagnose root causes, quickly pinpoint why an issue occurred, understand trends, plan for capacity, anticipate future needs, and identify long-term performance shifts. Validate optimizations, measure the impact of changes you make. Key metrics you should tirelessly track for your Redis instances include CPU utilization, both user and system CPU usage. High CPU on the main thread indicates Redis is processing a lot of commands or very complex ones. Memory usage, used memory, used memorious, memfragmentation ratio, and key space, number of keys, expiry information. Critical for capacity planning and detecting memory leaks or fragmentation. Network I/O, bytes received sent per second, vital for understanding traffic volume. Operations per second, OPS, total commons processed, instantaneous ops per sec, your primary indicator of Redis throughput. Latency, average latency, P99, 99th percentile latency, especially for client-side observed latency. High latency is often the first sign of trouble. Cache hit ratio. For caching use cases, this indicates how effectively your cache is serving requests. Replication lag. For master replica setups, the delay between master and replica. Critical for data consistency and failover readiness. Persistence status. RD blasts of time, AF current size, AF last write time sec. Ensures your data is being safely persisted. Number of connected clients. Helps understand demand and potential max clients issues. Number of evicted keys. Indicates if your max memory policy is actively evicting data. 11.2 Using the info command effectively. The info command, previously introduced in Chapter 4, is your built-in treasure trove of Redis metrics. It acts as a real-time snapshot of your Redis instance's health and performance. Info provides several sections, each focusing on different aspects. Info server, general information about the Redis server, version, uptime, port, configuration file. Info clients, details on connected clients, including the number of connections and inbound-outbound buffer sizes. Large output buffers for clients can indicate slow consumers or network issues. Info memory, critical for memory-related metrics, as discussed in Chapter 4, including used memory human, used memorious human, mem fragmentation ratio, and eviction statistics. Info persistence provides a quick overview of RDB and AOF persistence status, including last save times, rewrite operations, and AOF buffer details. Info stats overall statistics like total commons processed, instantaneous ops per sec, number of connections received, keys expired, and evicted. Info replication crucial for master replica setups, showing the role master replica, master link status, master repl offset, and connected replicas along with their repl offset, which indicates replication lag. Info CPU usage for the main Redis thread and background child processes. Info command stats statistics for each Redis command executed, including calls, total CPU consumed, and average CPU per call. Useful for identifying frequently used or heavy commands. Info cluster if part of a Redis cluster, shows detailed cluster health, nodes, and slot information. Info keyspace provides statistics about the number of keys and keys with expiration for each database. While you can run Redis CLI info manually, in production, you should automate the collection of info data. Monitoring systems typically pull the info command periodically, e.g., every 5 to 15 seconds, parse its output, store the metrics in a time series database, and then visualize them on dashboards. 11.3 Redis logs, the first line of defense. Redis logs provide valuable insights into the server's internal operations, configuration changes, warnings, and errors. They are often the first place to look when something goes wrong. Understanding different log levels, log level. Redis log level configuration parameter determines the verbosity of its logs. Debug. Very verbose, useful for development or debugging specific issues. Not recommended for production. Verbose, less verbose than debug but still quite chatty. Notice, default, moderately verbose. Records important events like connections, disconnections, persistence operations, and slow queries. This is generally a good balance for production. Warning, logs only critical errors and warnings. Too little detail for effective troubleshooting. You can configure the log file path using the logfile directive in redis.conf. What to look for in logs? Errors. Any lines starting with error, or panic. These often indicate critical failures or misconfigurations. Warnings. Lines indicating potential issues, such as high client connections, large memory usage, or CONFIG rewrite failures. Persistence events. Entries related to RDB saves, e.g. background saving started by PID. RDB. 0 MB of memory used by copy on write, AOF rewrites, and fsync issues. These are critical for data safety. Failover replication events. Messages related to master replica synchronization, sentinel role changes, or cluster reconfigurations. Client connection disconnection can reveal connection storms or misbehaving clients. Log rotation and management. In a busy production environment, Redis logs can grow very large very quickly. Implement log rotation, e.g., using logrotate on Linux, to prevent log files from filling up disk space. Integrate Redis logs with your centralized logging system, e.g., Elk Stack, Splunk, Datadog logs, for easier searching, analysis, and alerting across multiple instances. 11.4 Slow log. Identifying performance bottlenecks. The slow log feature is specifically designed to catch commands that take an unusually long time to execute on the Redis server itself, excluding network latency. It's a powerful tool for pinpointing inefficient queries that might be causing latency spikes for your application. Configuring slow log. Slow log slower than. Set the threshold in microseconds. For example, 1,000 logs commands taking longer than 1 millisecond. A sane starting point is typically 1,000 to 10,000. Slow log maxlen, the maximum number of slow log entries to keep in memory. A larger value uses more memory, but provides a longer history. Common values are 128 default to 1024. These are configured in redis.conf and can also be changed dynamically using CONFIG set. Analyzing slow query output. You can inspect the slow log using Redis CLI slow log get count. Each entry typically contains a unique sequential ID, the Unix timestamp of when the command was logged, the execution duration in microseconds, the command itself, including its arguments, the client's IP address and port, the client's name, if set by client setname. Actionable insights from Slowlog. Are keys or SMEMBRS HGTALL patterns appearing frequently? As discussed, these ON operations on large datasets are often the culprits. Consider replacing them with scan commands or redesigning your data model. Are specific Lua scripts causing issues? Long-running Lua scripts can block the server. Optimize the script or refactor the logic. Are commands on very large string values appearing? This could indicate network or memory issues. Are there unexpected commands? Check for debug commands or other administrative commands that shouldn't be run routinely. Regularly reviewing the Slowlog is key to proactive performance tuning. 11.5. External monitoring tools and integrations. While Info and Slowlog are excellent built-in tools for comprehensive production monitoring, you'll want to integrate Redis with external monitoring solutions. Prometheus plus Grafana. Prometheus, a powerful open-source monitoring system that scrapes metrics from various targets, including Redis exporters, stores them in a time series database, and provides alerting capabilities. Grafana, an open-source analytics and visualization platform. It connects to Prometheus or other data sources and allows you to create customizable, real-time dashboards for your Redis metrics. Integration. You typically run a Redis exporter, a small application, alongside your Redis instance. The exporter exposes Redis info metrics and other derived metrics in a format that Prometheus can scrape. This combination is highly popular for its flexibility and power in cloud-native environments. Commercial monitoring offerings. Many commercial monitoring platforms provide out-of-the-box Redis integrations with rich dashboards, advanced alerting features, and long-term data retention. Datadog, comprehensive monitoring, logging, and APM. New Relic, application performance monitoring with database insights. AppDynamics, similar to New Relic, focusing on APM. Splunk, primarily a logging platform that can also ingest and analyze metrics. Redis Insight for visual diagnostics. Redis Insight is an official GUI tool developed by Redis Labs. It offers a visual way to inspect memory usage. View info metrics. Analyze Slowlog entries visually. Browse and manage keys. Run ad hoc commands. It's an excellent tool for local development, debugging, and quick checks on production instances with appropriate security controls. 11.6. Troubleshooting common issues. Despite the best monitoring, issues inevitably arise. Here's how to approach common Redis problems. High CPU usage. Symptoms. High CPUSR or CPUSIs in info CPU, slow response times. Causes, inefficient commands, frequent ON operations, e.g., SMEMBRS on large sets, HGTALL on large hashes, or complex Lua scripts. Check Slowlog and info command stats. High TPS, transactions per second, simply processing too many commands for the single core. Consider scaling horizontally, clustering, or optimizing data model commands. Background saves. During RDB saves or AOF rewrites, the fork operation can temporarily increase CPU. Solutions. Optimize commands, use scan, pipelining, Lua for atomicity, redesign schema, scale Redis. Memory exhaustion. Symptoms. Used memory approaching max memory, memfragmentation ratio 1.5, OOM errors on write commands, potential swapping at OS level. Causes, max memory issues. Not set or set too high relative to available RAM. Memory fragmentation, Redis not reclaiming memory efficiently. Check memfragmentation ratio. Enable active defragmentation, Redis 4.0+. Large objects, too many large string values, hashes, or lists. Review data model. Memory leaks less common in Redis itself, misbehaving client buffers or internal Redis bugs. Solutions. Increase max memory, ensure active defragmentation, optimize data structures, evict old data, monitor used memorious. High latency. Symptoms. Application experiences slow responses from Redis, even if OPS is not saturated. Causes, network issues, high round-trip time RTT between client and server. Ping server, check network paths. Slow commands, specific commands blocking the server. Check slow log. Persistence events. RDB fork and save or AOF fsync equals always or eversec can introduce latency. Monitor info persistence. Long-running Lua scripts, blocking the event loop. OS-level issues. Swapping CPU contention from other processes. Solutions. Reduce network trips, pipelining, MGET, MSET, Lua scripts, optimize problematic commands, adjust persistence settings, address OS issues. Replication lag. Symptoms: master replofset versus slav replofset mismatch in info replication, stale data on replicas. Causes: network latency bandwidth, slow network between master and replica, slow disk on replica. AOF fsync or RDB save on replica can't keep up. Master overload. Master is too busy to send replication stream efficiently. Replica overload. Replica is too busy processing incoming commands or background tasks. Solutions: optimize network, use faster disks for replicas, vertically scale master replica, lighten replica load e.g., offload reads if high latency, verify replication settings. Connection issues. Symptoms: clients unable to connect, max number of clients reached messages. Causes: firewall, port blocked, wrong IP binding. Max clients limit, Redis max clients configuration, default 10,000 reached. Increase if needed, optimize client connection pooling. Misconfiguration, wrong port, IP, or authentication credentials. Client connection leaks, application not properly closing or releasing connections. Solutions: verify network configs, adjust max clients, review application code for connection management. 11.7 Backup and restore strategies. Data persistence methods, RDB AOF, prevent data loss during crashes, but they are not full backup solutions. A true backup strategy involves creating secure, externally stored copies of your data that can be restored in a disaster. Best practices for creating RDB snapshots. Redis's bgsave command forks a child process to create a point-in-time RDB snapshot without blocking the main server. Automate. Schedule regular bgsave commands, perhaps hourly or daily, via cron jobs or a dedicated backup tool. Offsite storage. Copy the RDB files to offsite redundant storage, e.g., AWS S3, Google Cloud Storage, object storage in your data center, immediately after they are created. This protects against server loss or data center-wide disasters. Retention policy. Implement a clear retention policy for your backups, e.g., keep daily backups for a week, weekly for a month, monthly for a year. Using AOF for recovery. While AOF offers higher durability, using it as your sole backup strategy can be risky if the AOF file becomes corrupted beyond automatic repair. AOF is primarily for recovery to the last known state after an unclean shutdown, rather than a point-in-time backup. You can periodically bgrewrite to compact the AOF file. Testing your restore strategy. A backup is only as good as its restore. Periodically perform doctor drills, disaster recovery drills, where you attempt to restore your Redis data from a backup to a new, isolated instance. Verify data integrity and completeness. Measure the recovery time objective RTO, how long it takes to recover. Measure the recovery point objective RPO, how much data you lost. This ensures your backups are valid and your restore procedures are sound. 11.8 Routine maintenance tasks. Proactive maintenance keeps your Redis instances running smoothly. Software upgrades, minor versus major versions. Minor upgrades, e.g., 6.0x to 6.2x, typically contain bug fixes and performance improvements, usually backward compatible. Follow official upgrade guides, test in staging, and plan for rolling upgrades in a cluster. Major upgrades, e.g., 5x to 6x, can introduce significant new features, breaking changes, or changes in data formats. Require thorough testing and careful planning, potentially involving a migration strategy. Always read release notes carefully. Redis daemon management. Familiarize yourself with starting, stopping, and restarting your Redis server daemon, Redis server. Ensure Redis starts automatically on system boot. Understand how to perform a graceful shutdown to ensure persistence files are written correctly. Cleaning up old keys. For volatile data, e.g., caches, session data, use expire with a suitable TTL. This is the primary way to manage old keys. For specific patterns of keys meant to be temporary, you might use client-side logic to del them. Avoid using del or unlink on excessively large sets of keys, as it can block the server. Memory defragmentation. Monitor the memfragmentation ratio metric from info memory. If it consistently stays above 1.5 to 2.0, it indicates significant memory waste. Redis 4.0 plus active defragmentation, if enabled and configured correctly, usually handles this automatically in the background. For older versions or specific needs, a planned graceful restart of the Redis instance can reclaim fragmented memory. By embracing a culture of continuous monitoring, proactive troubleshooting based on data, and diligent maintenance, you can ensure your Redis deployments remain performant, reliable, and secure for years to come. In the next chapter, we'll explore even more ways to extend Redis's capabilities using its powerful modules. Chapter 12. Advanced Redis modules and use cases. Redis offers a powerful and flexible core, but its capabilities extend far beyond the built-in data structures. Since Redis 4.0, the introduction of the Redis Modules API has transformed Redis into a multi-model database capable of handling a vast array of specialized workloads. Modules allow developers to extend Redis's functionality with new data types, commands, and functionalities, all while retaining Redis's characteristic speed and responsiveness. This chapter explores what Redis modules are, how to work with them, and then dives into specific, popular modules like Redis Search, Redis JSON, Redis Graph, and Redis Time Series, showcasing their powerful use cases and where they fit into modern application architectures. 12.1. Extending Redis capabilities with modules. What are Redis modules? Redis modules are dynamic libraries, written primarily in C, but can be in other languages that compile to C-compatible binaries that can be loaded into the Redis server at startup. They run directly within the Redis process, benefiting from its single-threaded, event-driven architecture. Modules can implement new data types with their own commands and persistence, add new commands that operate on existing Redis data types, introduce new functionalities like query engines, server-side processing, or external integrations. Loading and managing modules. Modules are typically loaded via the load module directive in the redis.conf file. Load module path to module so argument. For example, to load Redis Search, load module opt/redis modules/redis so. Once loaded, the new commands and data types become available just like native Redis commands. You can check loaded modules using the module list command in Redis CLI. Benefits of Redis modules. Specialized functionality. Modules often provide highly optimized, purpose-built solutions for problems like full-text search, graph queries, or time series analysis, which would be either impossible or highly inefficient to build using only core Redis primitives. C++ performance. Running directly inside Redis as compiled C++ code, modules offer near-native performance, on par with Redis's core commands. Closer integration. Modules have direct access to Redis's internal data structures and memory management, allowing for very tight and efficient integration. Simplicity and consistency. You manage these specialized data types and functionalities within your existing Redis ecosystem, simplifying your technology stack compared to deploying separate, dedicated databases for each specific use case. 12.2 Redis Search. Full-text search and secondary indexing. Redis Search transforms Redis into a highly performant full-text search engine and a powerful secondary indexing solution. It allows you to index data stored in Redis e.g., in hashes, and then perform complex queries at lightning speed. Concepts. Indexes. Redis Search creates an inverted index, much like traditional search engines. You define a schema for your index, specifying which fields from your Redis hashes are searchable, whether they are text, numeric, tag, or geofields. Documents. Data is stored in Redis typically as hashes. Redis Search indexes these document keys. Query language. Redis Search provides a rich query language to perform full-text searches, fuzzy matching, prefix matching, exact phrase matching, union, intersection, and numeric geospatial filtering. Commands: illustrative. ft create index name schema field name type property creates a search index. ft add index name docid score hash field value adds a document Redis hash to the index. ft search index name query string params performs a search query. Use cases: e-commerce search, allowing users to find products by name, description, category, or filter by price range and brand. Document retrieval, indexing articles, blog posts, or scientific papers for quick full-text search. Real-time inventory search, searching for products that are in stock by various criteria. Secondary indexing. Beyond full text, Redis Search can create secondary indexes on any field type, numbers, tags, enabling fast queries like find all users aged between 25 and 35 who live in New York. Performance considerations. Redis Search performs very complex operations entirely in memory. It is highly optimized for speed, but requires careful index design and can consume significant memory for large datasets, particularly with many text fields. 12.3 Redis JSON, native JSON document store. While you can store JSON strings in plain Redis strings, Redis JSON provides native support for storing, accessing, and manipulating JSON documents within Redis, treating JSON as a first-class data type. Concepts: JSON document storage. Redis JSON allows you to store entire JSON documents under a single Redis key. Path-based access. You can access, modify, and query specific elements within a JSON document using JSON path-like syntax. Efficiency. Operations on JSON documents are optimized, avoiding the need to fetch and parse the entire document client-side for simple updates. Commands: illustrative. JSON set key path value nx Roman 20 sets a JSON value at a specific path within a document. JSON get key path retrieves JSON values from documents at one or more specified paths. JSON ARRAPP and D key path value appends value to a JSON array. JSON.del key path deletes a JSON value at a specific path. JSON NUMINCRBY key path value increments a number at a path. Use cases: content management systems, CMS, storing and retrieving dynamic content fragments, product specifications, or user configuration settings as JSON documents. User profiles, storing flexible user profiles with nested data structures, e.g., addresses, preferences, historical data under a single key. Flexible document storage. Any application requiring a schemaless or flexible document model can leverage Redis JSON for fast access. Integration with Redis Search. You can index fields within Redis JSON documents using Redis Search, enabling powerful search capabilities on your JSON data. 12.4 Redis Graph, a graph database in Redis. Redis Graph is a graph database module that provides a lightning-fast solution for storing and querying graph structures directly within Redis. It leverages sparse matrices and linear algebra for its query engine, making it exceptionally fast for graph traversals even on very large datasets. Concepts: nodes, vertices, entities in the graph, e.g., users, products, cities, relationships, edges, connections between nodes, e.g., follows, BUIS, LOCATDIN. Relationships can also have properties. Cipher query language. Redis Graph utilizes a subset of the industry-standard Cipher query language, making it familiar to those with graph database experience. Commands: illustrative. Graph query graph name query string executes a Cipher query against a named graph. Graph.delete graph name deletes an entire graph. Use cases: social networks, modeling relationships between users, friends, followers, groups, and posts. Querying for friends of friends, or people who follow X and like Y. Recommendation engines, finding products similar to ones a user has bought or recommending new connections based on existing networks. Fraud detection, identifying complex patterns of interconnected entities that might indicate fraudulent activity. Knowledge graphs, representing complex interconnected data for AI or semantic search applications. Performance and scale. Redis graphs in memory. Sparse matrix-based engine often outperforms traditional graph databases for operations involving complex traversals and pattern matching. However, its memory consumption can be significant for very dense graphs. 12.5 Redis Time Series. Time Series Data Management. Redis Time Series is a dedicated module for storing and querying time series data efficiently. It is optimized for rapidly ingesting data points, performing range queries, and running aggregations over time intervals. Concepts: data points. Each entry is a pair of timestamp and value. Data aggregation. Supports various aggregation functions: average, sum, min, max, count, range, over specified time buckets. Downsampling automatically or manually reduces the granularity of older data to save space. Retention policies, configurable rules for how long data should be kept. Commands, illustrative, tscreate key retention time, labels label value, creates a time series. Tsadd key timestamp value labels label value, adds a data point to a time series. Timestamp can be for auto-generated. Tsrange key from timestamp to timestamp aggregation type time bucket, queries data points or aggregated data within a time range. Tsmrange queries multiple time series key in one call. Use cases: IoT sensor data, collecting and analyzing temperature, humidity, pressure, or energy consumption from sensors in real time. Financial data, storing stock prices, trading volumes, or other market data. Application metrics, monitoring system performance metrics, CPU, memory, network usage, logging application-specific events over time. Real-time analytics, building dashboards to visualize trends and anomalies in streaming data. Downsampling and data retention. Redis time series can automatically downsample old data, e.g., convert minute-by-minute data to hourly averages after 24 hours, and apply retention policies to delete data after a certain period, managing storage costs, and optimizing query performance for various granularities. 12.6 Exploring other notable modules. The Redis module ecosystem is vibrant and constantly growing. Here are a few more notable modules. Redis SQL, a module that allows you to store structured data in Redis as in-memory SQLite databases and query them using standard SQL. Useful for complex relational data that benefits from Redis's speed, or for migrating simple SQL workloads to Redis. Redis Bloom provides various probabilistic data structures, including Bloom filters, for probabilistic membership testing, already discussed in Chapter 2. Cuckoo filters, an alternative to Bloom filters, supporting item deletion and having a lower false positive rate for the same space. Countmin sketch, for estimating frequencies of items in a stream. TopK, for identifying the most frequent items in a stream. Redis AI, designed for deploying and serving pre-trained machine learning models directly within Redis. This allows you to perform real-time inference, e.g., image classification, recommendation scoring, as Redis commands, reducing data transfer overheads. 12.7 When to use a module versus external service. The availability of these powerful modules raises an important question. When should you use a Redis module, and when should you opt for a standalone, dedicated external service? E.g., Elasticsearch for search, Neo4j for graphs, InfluxDB for time series. Trade-offs: convenience versus specialized solutions. Module advantages: operational simplicity. You manage one Redis deployment instead of multiple disparate systems. Simplified setup, monitoring, backup, and scaling using existing Redis tools and expertise. Performance: modules benefit from Redis's in-memory speed and efficient internal mechanisms. Data locality: data is stored in Redis, so modules can operate on it directly without network transfers. Cost efficiency: potentially lower infrastructure costs by consolidating services. External service advantages: maturity and feature richness. Dedicated services are often more mature, have a broader feature set, and larger, more specialized communities. Scalability for extreme workloads. For truly massive or highly complex workloads, e.g., petabytes of time series data, federated graph queries across multiple sources. A dedicated, distributed system might offer better horizontal scalability and resilience. Separation of concerns. Some prefer to keep specialized functionalities separate for architectural clarity. Considerations. Workload characteristics. Is the specialized function a primary part of your application or a secondary one? If it's central, a dedicated service might be appropriate. If it's an auxiliary function that benefits from shared data with other Redis-served functionality, a module could be a great fit. Data volume. How much data will you be pushing through this specialized module? While modules are performant, massive datasets might stretch Redis's single-threaded capacity or memory limits. Community and support. Consider the module's maturity, community support, and whether commercial support is available, e.g., Redis Enterprise often includes support for popular modules. Complexity. How complex are the queries or operations you need to perform? For very advanced features of a specific domain, a dedicated service likely offers deeper capabilities. In many cases, Redis modules provide an excellent 80-20 solution. They cover 80% of the common use cases, with 20% of the operational overhead of a dedicated specialized database. They are particularly attractive for applications that already rely heavily on Redis for other use cases. By carefully evaluating your exact needs, you can decide whether a Redis module or an external service is the better choice for your application. The final chapter will bring all these considerations together, focusing on how to successfully deploy Redis in production environments. Chapter 13, Deploying Redis in Production. Successfully deploying Redis in a production environment is the culmination of understanding its architecture, optimizing its performance, leveraging its patterns, and securing its operations. This final chapter ties together many previously discussed concepts, providing practical guidelines for choosing the right deployment environment, setting up for high availability and scalability, configuring for optimal performance, and planning for ongoing maintenance and disaster recovery. 13.1. Choosing your deployment environment. The first critical decision is where and how to run your Redis instances. Your choice will impact operational overhead, scalability, cost, and control. On-premise, your own data centers. Pros: maximum control over hardware, network, and security, potentially lower long-term costs for very large scale. Cons: high initial investment, hardware, infrastructure. Significant operational burden, power, cooling, maintenance, patching, scaling, disaster recovery. Best for organizations with specialized hardware needs, strict data residency requirements, or existing large data center footprints and expertise. Cloud infrastructure as a service, IaaS like AWS EC2, Azure VMS, GCP Compute Engine. Pros: flexibility in choosing VM sizes, operating systems, and network configurations. Pay-as-you-go model, easier to scale resources up-down. Cons: you're still responsible for installing, configuring, managing, patching, and securing Redis and the OS. May not be cost-effective at very large scale compared to on-premise without heavy optimization. Best for teams that want control over their Redis setup without owning physical hardware, or for custom setups not available as managed services. Containers, Docker, and orchestration, Kubernetes. Pros: portability, run Redis consistently across dev, staging, prod, resource efficiency, rapid deployment and scaling, self-healing capabilities with orchestration. Cons: adds a layer of complexity, containerization, orchestration, platform management, requires expertise in Docker and Kubernetes. Best for modern cloud-native applications, microservices architectures, and DevOps-centric teams looking for automation and efficient resource utilization. Managed Redis services, database as a service DBaaS. Examples: Amazon Elasticache for Redis, Google Cloud Memory Store for Redis, Azure Cache for Redis, Redis Enterprise Cloud. Pros: significantly reduced operational burden, vendor handles patching, backups, replication, failover, scaling, monitoring. High availability and resilience built in, often lower TCO, total cost of ownership, as you pay for the service, not the management overhead. Cons: less granular control over Redis configuration, potential vendor lock-in, higher operational cost for very high usage compared to self-managed, sometimes limited to specific Redis versions or features. Best for most organizations that value operational simplicity, rapid deployment, and focus on application development rather than database management. 13.2 Deploying with Docker and Kubernetes. Containers provide a lightweight and consistent way to package and run Redis. Kubernetes, as a container orchestration platform, automates the deployment, scaling, and management of containerized applications, including Redis. Running a single Redis instance in Docker. Simple Docker run name myredis. P6379, 6379D Redis, latest gets a basic instance running. For persistence, map a host volume. Docker run name myredis. P6379, 6379 vpath/on/host/data/data d Redis, latest Redis server appendedly yes. This ensures data persists if the container is restarted or deleted. Orchestrating Redis with Docker Compose. For multi-container applications, e.g., app plus Redis, Docker Compose YAML simplifies defining and running the services together. You can declare network dependencies, volumes, and environment variables. Deploying Redis in Kubernetes. Stateful sets. For stateful applications like Redis, Kubernetes stateful sets are the go-to. They provide stable network identities, ordered scaling, and graceful deployment deletion, crucial for managing a Redis cluster or replicated instances. Persistent volumes, PVS, and claims, PVCS. Ensure your Redis data is durable by provisioning persistent volumes through persistent volume claims. These abstract underlying storage, e.g., EBS, NFS, and ensure data survives pod restarts. Headless services. For Redis cluster, headless services can be used to manage network access to individual pods while still allowing the cluster members to discover each other via DNS. Kubernetes operators for automated management. For complex Redis deployments, e.g., Redis cluster, Sentinel, a Redis operator can automate many day 2 operations like scaling, upgrades, and failover. These operators encapsulate expert knowledge of how to run Redis clusters on Kubernetes reliably. Examples include Redis Operator by Spot.io or similar solutions. Considerations for Kubernetes. Persistence. Ensure your PVs are highly available and backed by reliable storage. High availability. Deploy Redis Sentinel or Redis cluster using stateful sets to manage multiple pods across different nodes for redundancy. Configure anti-affinity rules to spread Redis pods across different physical nodes. Networking. Understand Kubernetes networking for interpod communication and service exposure. Configuration management. Use Kubernetes config maps for Redis.conf and secrets for authentication details. 13.3 Considerations for cloud deployments. Managed Redis services offer significant advantages in the cloud. However, if you opt for self-managed Redis on cloud VMS, consider leveraging managed services. Benefits. Drastically reduced operational overhead, automatic backups, patching, scaling, often one click, integrated monitoring, and high availability. Drawbacks. Less control over Redis version and configuration, potential vendor lock-in, and cost model might be higher for very large-scale, bursty, or idiosyncratic workloads. Choosing instance types, network configurations. Instance type. Select VM instances with sufficient RAM, good CPU performance, especially single-core speed for Redis main thread, and optimized network throughput. Memory-optimized instances are often a good starting point. Network configuration. Place Redis instances and client applications within the same availability zone, or even host, if possible to minimize network latency. Use private IP addresses and security groups for secure, isolated communication. Cost optimization techniques. Right sizing. Continuously monitor resource usage, info command, external tools, to ensure you're not over-provisioning. Reserved instances savings plans. For predictable, long-term workloads, commit to reserved instances to lower computing costs. Eviction policies. Effectively use max memory and eviction policies, Chapter 4, to manage memory and prevent unnecessary scaling out if your cache can tolerate eviction. 13.4 Capacity planning and sizing your Redis instances. Accurate capacity planning is crucial to avoid performance bottlenecks, ensure stability, and manage costs. Estimating memory requirements. Key space. How many keys will you store? What are their average sizes? Debug object for individual keys. Redis CLI big keys to find large keys. Value sizes. How large are your typical string values or the elements within your data structures? Data structure overhead. Hashes, lists, sets, sorted sets, and streams have internal overhead. Redis is memory efficient, but large numbers of small items can still add up. Replication buffer. Master nodes need memory for replication output buffers for replicas. AOF buffer. If AOF is enabled, the AOF buffer also consumes memory. Fork overhead. During RDB saves or AOF rewrites, the fork operation requires memory copy on write. A ballpark estimate is 2x the memory used by your dataset. Rule of thumb. Plan for at least 2 to 3x your estimated dataset size as your instance's RAM. Keep a buffer for unforeseen growth and operational overhead. Predicting CPU and network throughput. CPU. Estimate your desired operations per second, OPS. A single Redis core can typically handle 50K, 150K ops depending on command mix. Benchmarking, Redis benchmark, with your actual command mix is key. Network, estimate inbound and outbound bandwidth based on average value sizes and OPS. Large values or frequent SMEMBRSHETLL can quickly consume bandwidth. Load testing and stress testing. Use tools like Redis benchmark, Memter benchmark, or custom application-level load tests, e.g. JMeter, Load Runner, to simulate peak production load on your Redis instances. Goals. Validate your sizing estimates. Identify performance bottlenecks, CPU, memory, network. Test your replication, sentinel, and cluster failover capabilities under stress. Uncover edge cases and stability issues. Scaling up versus scaling out. Scaling up vertical, increase RAM CPU on a single instance. Simpler, but limited by hardware ceiling and leaves a single point of failure. Good for initial growth. Scaling out horizontal. Add more instances, replication for reads, clustering for sharding. More complex but provides greater scalability and high availability. Essential for large datasets or very high throughput. 13.5 Configuration, best practices for production. The redis.conf file is central to your Redis deployment. Here are critical settings for production. Daemonize yes, runs Redis as a background process. pidful/var/run/redis 6379. PID specifies the file where the process ID is stored. Logful var/log/redis/redis server log specifies the log file. Use notice log level for production. Also consider log rotation. dir/var/lib/redis directory where RDB and AOF files are stored. Ensure this directory has sufficient disk space and appropriate permissions. TCP backlog 511. Default 511, the maximum number of pending connections. Increase if clients frequently hit connection refused. Timeout 0. Default 0, client inactivity timeout. Set to 0, no timeout for persistent connections or a low value for web-facing services to prevent idle connections from consuming resources. Security configurations, covered in Chapter 10. Bind, essential for network isolation. Require PAS, if not using ACLS, set a strong password. ACL users, ACL SETUSER commands in an ACL file. For granular access control, rename command to disable rename dangerous commands. TLS port and related TLS settings for enabling TLS. Persistence configurations, covered in Chapter 4. Choose between RDB, AOF, or both, appendantly yes. Tune RDB snapshot policies, save 901, save 310, etc. Tune AOF fsync policy, append sync eversec is usually a good balance. Memory configurations, covered in Chapter 4. Max memory, crucial for setting a memory limit. Max memory policy, choose appropriate eviction policy, all keys LRU or all keys LFU for caching. Active edifrag yes. Enable active defragmentation, Redis 4.0+. Replication cluster specifics, replicaoff masterip masterport for replicas, Cluster-enabled yes for cluster nodes. Cluster config file, where cluster state is stored. 13.6 Release management and version control. Managing Redis software versions is critical for stability and accessing new features. Planning for Redis upgrades. Read release notes. Thoroughly understand changes, new features, deprecations, and potential breaking changes. Test in staging. Never upgrade Redis directly in production without extensive testing in an environment that mirrors production or is production-like. Test your application against the new Redis version. Replication and cluster upgrades. Follow specific upgrade procedures. For a cluster, this typically involves upgrading nodes one by one, ensuring continuous availability. Canary deployments, blue-green deployments. While more common for application code, you can apply similar principles to Redis upgrades or reconfigurations. Canary. Roll out changes to a small subset of traffic users first. Blue-green. Maintain two identical environments. Switch all traffic to the new one after verification. These methods minimize risk but add complexity. Rolling updates for clusters. In a Redis cluster or Sentinel setup, upgrades are usually performed via rolling updates, where nodes are upgraded one at a time to maintain service continuity. 13.7 Disaster recovery planning. A comprehensive disaster recovery doctor plan goes beyond just backups. It outlines how to restore service entirely after a major outage, e.g., data center failure. Beyond backup and restore, full doctor strategy, high availability, your HA design Sentinel cluster should be the first line of defense, handling most node failures. Backup strategy. As discussed, RDB plus AOF backups to offsite storage. Automated recovery. Can you automate the process of provisioning new Redis instances and restoring from backups? Documentation. Clear, up-to-date runbooks for recovery procedures. RTO, recovery time objective. The maximum acceptable duration of time that a Redis service can be unavailable after a disaster. Your HA design and doctor plan should aim to meet this RTO. RPO, recovery point objective. The maximum acceptable amount of data loss measured in time. This is directly tied to your persistence strategy. AOF with Eversec provides lower RPO than daily RDB snapshots and backup frequency. Multi-region deployment strategies. For the highest level of disaster recovery and global presence, consider multi-region Redis deployments. This can involve active-passive setups, one region active, others standby or active-active, traffic split across regions. Implementing multi-region deployments for data consistency is complex and often requires additional tools or custom application logic. 13.8 What's next for Redis and your learning journey? The Redis ecosystem is dynamic and constantly evolving. New versions introduce performance improvements, new data structures, modules, and operational enhancements. Brief look at upcoming features or trends. Enhanced multi-threading. While core command execution remains single-threaded, Redis continues to explore safe ways to offload more I/O and background tasks to multiple threads for even higher scalability. New modules. The module ecosystem will continue to grow, offering more specialized functionalities. Cloud-native adoption. Continued focus on making Redis easier to deploy and manage in Kubernetes and serverless environments. Redis as a unified data platform, expanding its role beyond caching to a multimodal data platform for diverse workloads. Encouragement for continued learning and experimentation. Mastering Redis is an ongoing journey. The best way to stay current is to follow the official Redis blog. Redis.io/blog provides updates and deep dives. Participate in the community. Engage in forums, Stack Overflow, Reddit r/Redis, attend conferences, RedisConf. Experiment, set up local Redis instances and test new features, modules, and configurations. Read documentation. The official Redis documentation is comprehensive and constantly updated. By diligently applying the principles and practices outlined in this book, you are now well-equipped to design, implement, optimize, secure, and operate Redis deployments that are performant, resilient, and ready to meet the demands of modern applications. Your journey into mastering Redis has just begun.